Hello Cloud Gurus and welcome to this lesson during which I'll detail the second case study we'll be using in this course, Cody's Development LLC. Cody's Development LLC is a software development business, so it will have different needs and requirements from the previous case study, which was WordPress Hosted Incorporated. Let's jump into the introduction and look at the needs in more detail. So this is the second of two case studies that will be used within this course, and it will introduce a number of advanced key ideas and concepts. Cody's Development LLC is a traditional software development company. They write a number of applications, but one specific one is a building and facilities management application for large enterprise and government. The company consists of 150 employees, 40 of which are developers. The remaining employees are a mixture of pre-sales, general business admin and financial personnel, application testing, customer support and installation engineers. This means the development staff are over 40% of the company by staff count, and 25% are application testing engineers. Now the company has a number of key pain points. The testing process is limited and inefficient due to the use of internal hardware, and the sales team struggle to provision demo environments in a timely manner to perform pre-sales walkthroughs. Now they currently develop their application for hosting on customer on-premise servers, but they're looking at moving to a hosting or SaaS style model where they host and support the software running within a Cody's managed AWS environment. The business has identified that if it can improve its development and testing processes through automation, they can achieve significant cost savings to the business, and this will potentially change the internal staffing model. Additionally, if the user base can be moved from on-premise installs towards SaaS, then the company's installation and support engineer headcount can be moved into development and testing roles. They have a long-term requirement that we as consultants assist them with the CloudFormation assets to provision and control the SaaS environment. But they also have two immediate short-term requirements, namely that we provide assistance with automating their testing processes, and we provide assistance with the automated provisioning of pre-sales environments. Let's step through both now so we know what's involved. Now as above, we have 40 development staff. All of these engineers work on the same code base, which is stored within a private online GitHub repository. These engineers are acutely aware of their lack of real testing within the business, so tend to check out code, work on it for 1 to 3 days depending on the feature size, and then push the code back into the repository. And they do so without using feature branching. It's all on the master code branch. Immediately we have a problem here. Integration hell. We have 40 developers checking out of the same code base, working in isolation on separate sections, and then pushing the same code back into the repository. Even assuming that we don't have conflicts, which we will, none of the new blocks of code have been tested with the blocks of code being edited by other developers. We have pretty much no integration testing. There is normally a 1 to 3 day period between major testing, and let's talk about this next. Every 1 to 3 days, the business testing team takes a version of the code from GitHub and downloads it into the testing environment. The testing team have a number of on-premise servers allocated to testing, anywhere between 1 to 3, depending on the pre-sales requirements, and more on this in a second. The important aspect to this process is that the testing team have to either 1, test the code version on an existing server, which potentially has remnants of an older version of the app, or 2, rebuild the entire server complete with all dependencies, and this takes time. Both of these are less than ideal and explain why there have been more and more complaints regarding bugs in recent software versions. An added complication is that the pre-sales team are often asked for demo environments for customers and often need to request this weeks in advance. Since there are no dedicated internal servers for pre-sales, the hardware required is often stolen from the testing pool. This takes time and it reduces the effectiveness of the testing team. It also provides substandard service to the pre-sales team who are fighting for sales, and the availability of a demo environment significantly influences the success of their processes. So where do we want to get to? Let's have a look on the next slide. So starting with the development side, we know we have 40 developers, but that's not easy to represent on screen, so let's go with 8. Assume that each one on the screen represents 5 real developers. We also have GitHub, and this is where our central code is stored for the application. This is where we want to change the process. Our ideal approach is that we have all the developers working from the repo at all times, syncing their code as often as possible. As each of these developers work, they would push their changes into the repository, and each time this occurred, there would be a set of automated tests occurring on their code, simple linting, base syntax checking, and other automated processes. As part of this process, we've been asked to create a set of CloudFormation templates to support the next step of the process. And these templates for the production system will be stored within the GitHub repository. But what happens next is the clever bit. As part of every major code change, the CloudFormation template is used to automatically spin up an entire test environment based on the latest code committed to the repository. Now in production, this could be done manually using the CloudFormation template or using a tool such as Jenkins, or a combination of code commit, code pipeline, and code deploy tools. Whatever the tool choice, an isolated, completely functional environment is created based on the code commit, complete with any AWS infrastructure components, instances, load balancers, and other application components. Automated testing runs within this temporary environment, after which the whole infrastructure set is deleted and cleaned up. Using this process, we can achieve a full continual test, integration, and deployment process, where every commit to the repository is tested, integrated with other changes, and tested again. And finally, it's deployed into a fully working environment for interactive, human user acceptance testing, all without running any base level infrastructure. Equally, the same process can be used for the pre-sales team. Let's assume they're at a client site and have received a request for a test environment running version 3.2 of the code. Now we've established this system, they could log into a web interface, select code version 3.2, and have an entire working demo environment provisioned within minutes, and this can be provided to a customer for evaluation. Now, as you can see, with some small changes, the ability for Cody's development to improve their internal process effectiveness is substantial. And that's what we'll be looking at together during this section, how we can leverage the features of CloudFormation to allow this business change, to allow this automation. This section will include theory, introducing the concepts, and demos where we will together explore the ways in which these features can be utilized. Well, that's the end of this lesson where we've discussed the structure of this section. If you do have any questions on this lesson or any others, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus, and welcome to this lesson within which I'm going to talk about the base infrastructure within which Cody's Development LLC is going to deploy the application instances, either for testing or pre-sales purposes. Let's jump right into it. In the previous case study, WordPress Hosting Incorporated, we made use of the default VPC to implement our hosting product. While that works, I tend to avoid using the default VPC for production purposes. I like to keep it clean and unused within any AWS environments with production workloads. There are a number of issues which can impact your environment if the default VPC is changed or removed, issues which will require the involvement of AWS support to resolve. Rather than risk this, I find it's better to create the resources required for any projects externally to the default VPC, and that's what we'll do together in this case study. So the first thing that we'll need, logically, is a VPC for the whole project. Now we could have a number of VPCs, perhaps one for development, one for testing, one for pre-sales, and finally one for production. To keep things simple and to keep costs down for this case study, we'll use one VPC to home all 4 of those use cases. We should also know that a VPC needs an IP range, also known as a CIDR range, and this CIDR range is assigned to it when we create it. And so our base infrastructure template will do this. It will create a VPC and assign a CIDR range. Within this VPC and the wider AWS environment which it sits in, you will have a number of availability zones, and these can number anywhere from 2 to 5, depending on when you watch this. As we're using the same template for all use cases from dev to production, it will need to be capable of some form of HA. So we will need to utilize multiple availability zones. I could go crazy and use them all, but again, I want to keep things simple and economical for this proof of concept case study, so I'm going to stick with 2. Let's not worry about which AZs they are for now, we'll just refer to them as AZA and AZB. Within our base infrastructure VPC, we're also going to have 2 zones. Now these zones aren't AWS resources or concepts. I just want you to get used to conceptually thinking of things in this way. First, the external or public facing zone, and secondly, the internal or private zone. Within our public zone, we'll create 2 subnets, one in each of the availability zones. and these will function as public shared infrastructure subnets. We know they'll be public because we'll create an Internet Gateway object in this VPC, and our public subnets will have default routes associated and pointing to this Internet Gateway. Within these public shared infrastructure subnets, we'll also create a pair of NAT gateways. NAT gateways are managed products which provide internet access to any machines within the VPC which don't have direct public access, essentially any private instances. And we'll use a pair of NAT gateways to ensure HA. So we're separating the fault domains. We've got a fault domain in AZA and a fault domain in AZB. So if either of those die, we'll still have Internet Gateway and NAT Gateway functionality. Now, both of these NAT gateways will need elastic IPs, and elastic IPs, as we should know by now, are public static IP addresses provided by AWS. It's these IPs that will be used to NAT outgoing traffic via the NAT gateways. Think of the NAT gateways as similar to home internet routers if you don't understand the concept of NAT. Either way, I'll add a link to your screen now, providing a brief high-level overview of the NAT process, or network address translation. Once we have this infrastructure configured, we can deploy other things into it, and this is done by creating private or public subnets in the private or public zones, and this is indicated by the yellow block on your screen now. We'll need to create those subnets and routing to allow this, but more on this shortly. Internet access can be obtained via the Internet Gateway for the public subnets, which is HA by design, or via the NAT Gateway for the private subnets. So just to reiterate, within the shared services or shared infrastructure VPC, we've created the shared infrastructure necessary to provide public subnets and private subnets with internet connectivity. And we're allowing within that yellow block that you can see on your screen now, other subnets to be created within it. And we'll talk more about what these other subnets might look like when we talk about the application infrastructure. And you might notice that we don't have any application infrastructure yet, no app servers, and that's by design. Let's move on to the next slide and discuss this in a little bit more detail. I want to introduce a best practice concept that we'll use throughout this section, and that's using multiple stacks. And we use multiple stacks to separate infrastructure either by team role or by lifecycle. It's a concept which will make the ongoing management of large infrastructure sets significantly easier. The traditional and simpler way of managing infrastructure via CloudFormation was to add everything into one stack. So in this example, both the application and its supporting infrastructure would be managed within one template and one stack. The entire sum of resources, so the application and its supporting infrastructure, would have only one lifecycle, and it would be managed as one unit. The problem with this method is that the entire collection of resources falls within one risk, control, and permissions domain. Edits to the template when you're performing an application add, remove, or modify would add risk to the whole stack. You would need to apply change control and permissions to the entire stack, possibly limiting the velocity at which your developers could deploy new versions or changes. Remember, a key requirement for this case study is to support a better, more agile, and more reliable code testing, deployment, and pre-sales process. Adding an unnecessary link between the change control processes of the infrastructure and the application code is counterproductive. Remember, the change control process is traditionally more rigorous for infrastructure than it is for code updates. So how do we manage this? As I alluded to a few sentences ago, we do a stack and template separation. And we can separate this based either on roles, so staff, individuals, or teams, or we can separate them based on the risk or life cycle of the resources being managed. In this case study, we have two obvious groupings of people. We have operations staff, and we have devs or pre-sales. The former are concerned with stability, security, and control. They minimize velocity to ensure stability. The latter are much more concerned with the velocity of changes. Devs want to commit as regularly as they can, and they want to get every commit tested without any artificial restrictions. The pre-sale staff need to be able to provision new infrastructure on short notice to assist them with winning customer opportunities. We have two obvious lifecycle sets. The first is the base infrastructure, which we discussed on the last slide. It's fairly static, and it's essential for the reliability of the app, and it needs to be under tight operational control. But we also have the application, which is likely to be instantiated and torn down regularly with much less control, and this allows the smooth running of the other business processes, so development, testing, and customer engagement. Based on this, it makes complete sense to take our single template and stack and split this based on the nice infrastructure and app lifecycle division which we have. That way, we can have updates applied to either the infrastructure or the app stack in isolation, and we can have separate people with the permissions or authorization to do each also in isolation. But also, it gives us the ability to have separate stacks for the application, so we can have one application instance per stack. And that gives us much better flexibility with the automated deployment and cleanup of the individual app instances. If we're deploying a separate stack every time we deploy a single app, so a single app for pre-sales or a single app for testing, it means that those individual infrastructure groups are completely isolated and separate. So that will be our initial architecture. One template and stack for the shared supporting infrastructure, which we've already discussed, and one template for the application environment, which will be instantiated any number of times depending on the development and pre-sales needs. Well, that's the end of the theory and discussions around the shared infrastructure configuration. And about the best practice role and lifecycle based stack separation we'll be employing within the rest of the case study. If you do have any questions on this lesson or any of the others, then please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus and welcome to this demo lesson, the first of the demo lessons in the Cody's Development LLC case study. Now in this demonstration lesson, we're going to look at the shared services or shared infrastructure stack. In the last lesson, a theory lesson, I stepped you through the components of the shared infrastructure stack, and I described at an architectural level why the shared infrastructure stack existed. The shared infrastructure stack provides resources necessary to deploy within it application environments. So this shared stack contains a VPC, it contains subnets, it contains route tables and routes, internet gateways, NAT gateways, and other networking configuration and resources required to allow the instantiation of resources which have network connectivity. So in short, this stack is going to provide the network services which are consumed by the application stack, and we'll define what the application stack entails in the next lesson, and we'll follow that up with a demo lesson similar to this where we demonstrate how it's implemented. So the first thing I need you to do is to log in to the AWS console using the account that you created for this course. And secondly, we need to go to the lessons file folder. Now, as always, you'll either have downloaded the lesson files for this specific lesson from the resources section of the Cloud Guru website, or you'll have downloaded the entire lesson files for the course from the GitHub repository. In either case, you're looking for the 201 shared infrastructure folder, and within that folder, shared infrastructure.yaml or shared infrastructure.json. When you're taking the course, there'll be two templates, one YAML and one JSON. I'm going to be using the YAML version as the primary version for the remainder of this lesson, but you're free to read through and apply the JSON template if you wish, but I strongly suggest that you continue using the YAML versions of the template, as that's what I'm going to do in these demo lessons, and it makes it easier for you to follow along. Okay, so let's get started. The first thing is to open the shared infrastructure.yaml file. Okay, so there's a number of things that I want to draw your attention to in this template. The first are the three parameters that we've got. We've got the VPC CIDR block to use, and this is the /16 IP address range that the VPC that we're creating specifically for this case study will use. Now it's set as default to use 10.20.0.0/16, and my hope is that this IP address range won't conflict with any ranges that you have in other environments, other VPCs, or within an existing corporate network if you're applying this into a multi-use case account. Now, as discussed in the last lesson, inside this shared infrastructure VPC are two shared public subnets. And just like the above parameter, we're defining the CIDR block used for each of these public subnets. We're using /22 IP address ranges, and the default IP address ranges are 10.20.0.0 and 10.20.4.0. And if you've got some networking experience, you'll see that both of those are valid subnets of the wider VPC CIDR block. And that's by intention. It has to be the case. Any subnets that are declared inside of VPC need to be subsets of the IP address range assigned to the VPC. Now, moving further down, most of what you see should be familiar by now. We're declaring a VPC and we're referencing the VPC CIDR parameter. We're declaring an internet gateway, an S3 bucket, which is where the application and test payloads of our application will be stored, and more on this in the next lesson. A policy for that bucket, a gateway attachment, which defines how the internet gateway is attached to the VPC. We're declaring the public shared subnet A and B, and each one of those is in a separate availability zone. And we're using runtime selection. So we're listing the availability zones in the region where we are using the getAZs function. And we're selecting the first of these for the availability zone of shared A. And then likewise, shared B selects the second of the availability zones. And we're referencing the parameters p shared A CIDR and p shared B CIDR, which are the parameters declared at the top of the template. And they contain the CIDR ranges for both public A and public B shared subnets. And then below that, we have route tables, we have subnet route table associations, we have elastic IP address ranges, which the NAT gateways will use. We've got the NAT gateways themselves, which provide internet access for any private instances or instances in the private subnets, and they'll be used by the application environments, which we'll talk about shortly. And lastly, we've got the outputs for this template. And the outputs list the VPC ID for the VPC which gets created, the IDs of the NAT gateways, so that's NAT gateway A and NAT gateway B. We also provide the ID of all of the route tables, so the public route table and the private route tables. And lastly, we have the application bucket URL, which is the URL of the bucket which holds the application and test payload files, and they'll be used by the application environment template, which we'll discuss in a future lesson. So in summary, there's nothing complicated about this template. Nothing in this template should concern you, and it should all be review or revision at this stage. What I want to do is apply the template and step you through what happens during its creation, and then briefly talk about the infrastructure that's created as a result of the stack creation. So let's go back to the AWS console and we'll implement this together. Now I do want to mention that this shared infrastructure template and the stack that it creates will be used on an ongoing basis throughout this lesson. You can either upgrade the stacks between the lessons, so when we move on to the next version of this, you've got the option of upgrading it, or you can delete the shared infrastructure stack at the end of every lesson and recreate it with the newest version when we start the following lesson. The choice is yours, and if at any point I've got certain requirements, I'll stress those at the start of the lesson. So first, management tools and CloudFormation. And let's just go to the CloudFormation console. And hopefully you cleared up after the first section and your CloudFormation console is completely fresh. As always, I suggest that you use the North Virginia region. You should be able to use a region closer to your physical location, but this is the region that receives the majority of the testing as part of the course development. You will find that most regions function just fine, but if there are any regions which lag behind in terms of features, you could have some problems. So I'll leave it with you to make the decision whether to use North Virginia or something else. So let's begin. Create new stack. Click on Upload a template to S3 and click Choose File. Locate where the course downloads are. And as discussed a second ago, you're looking for the 201 shared infrastructure folder. Select the shared infrastructure.yaml template and click on Next. And just review these parameters. So you've got the VPC CIDR range, which is 10.20.00/16. And then within that VPC CIDR range, you've got the 2/22 public shared subnets. And at this stage, the only thing occupying them is the NAT gateways. The NAT gateways are going to live one in the shared subnet A and one in the shared subnet B. And the important thing to grasp is that both of these CIDR ranges live inside the range for the VPC. So go ahead and name your stack shared infrastructure. And then click on Next. We're not going to apply any stack roles or configure advanced options, so click on Next again. And it's not creating any IAM users or roles, so there'll be no IAM warning or IAM capability to accept. We can just go ahead and click on Create. Now this process could take between 5 and 10 minutes. While you're waiting, click on the Events tab and just keep refreshing, and you'll be able to see one by one all of the resources being created. You'll notice VPCs, S3 buckets, internet gateways, NAT gateways, route tables, subnets, the associations between those. There'll be many resources. I think there's a total of about 19 resources that get created in total. It should take about 5 to 10 minutes, as I mentioned a second ago. I'm going to pause the video and resume once the creation's completed. You have the option of either sitting watching the process end to end, or you can use the opportunity to go and make a coffee or get a bite to eat. Either way, I'll pause the video and resume once we've got some progress. Okay, so the shared infrastructure stack is now in the create complete state. We can click on the resources tab and see all of the resources that have been created as part of the stack deployment. We've got the bucket policy, got elastic IPs, gateways, NAT gateways, routes, the S3 bucket itself, the VPC. As mentioned, we've got about 19 resources in total. If we click on the outputs of the stack, we can see that we've got the IDs of all of our route tables, the private and the public. We've got the IDs of the NAT gateways and the VPC, and then the URL of the application bucket. Now, all of these outputs are going to be consumed by the application environment template, and that's the reason why we've got them in the outputs. It's going to be quite some work transferring these values into the application environment, and at this stage, it's all going to be manual. But just keep in mind that when we do apply the application environment, we'll need a lot of these outputs. Now, there are a few things to understand about the shared infrastructure stack. The first thing is that the life cycle of this stack will be fairly rigid. It's going to be instantiated generally once, and I don't imagine outside of what we're doing within this course, so evolving it, I don't feel there'll be many changes. It contains only the networking and networking infrastructure required to support the application environment, so we won't see many changes. And as part of this case study, what we need to look at is that this stack will be managed by the networking or infrastructure team, and it can be done so using formal and rigid change control processes. The changes, so the rapid creation and deletion that will be forced on us by doing the workflows mentioned in this case study, so the development and the pre-sales deployment, they'll occur outside of the scope of the shared infrastructure template. The shared infrastructure template can therefore form part of a rigid change control process, whereas the application environment will need to be part of a more agile and less structured process. And that's the key thing, this separation of requirements and separation of roles between the staff who will manage the shared infrastructure and the development team who will look after the application environment. The application environment has an agility requirement. Environments will be instantiated and deleted fairly commonly, both from a development perspective and from a pre-sales perspective. So it was essential to separate the slow-moving, slow pace of change and rigid control of the shared infrastructure and the agile, ever-changing nature of the application environment. So that's the end of this demonstration lesson. Do feel free to open the services menu and locate VPC. Open it in a new tab maybe and step through and look at all of the different pieces of infrastructure that have been created as part of this shared infrastructure stack. We've got a VPC in here, we've got subnets, internet gateways, NAT gateways. Step through and just familiarize yourself with each of the individual components. You'll see that throughout this section, we're going to evolve the shared infrastructure template and we're going to evolve the application environment template. So be aware of what this initial version, version 1, what infrastructure components it creates. It's definitely worth spending the time at this stage becoming familiar and comfortable with what elements are created by each of the stacks that we're working with. Okay, so that's the end of this lesson, Cloud Gurus. Thanks for listening. As I mentioned at the start of this lesson, you can either leave the shared infrastructure template in place, or you can remove it at the end of every lesson and recreate it at the start. The choice is yours. If I don't mention otherwise, assume at the start of every lesson that you need a created and working shared infrastructure stack to be able to complete the rest of the lesson. All of the follow-up lessons that we do will need the infrastructure components provided by this stack. So if you do delete it, do remember to recreate it at the start of every applicable lesson. Now, if you do have any questions about this lesson or any others, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus and welcome to this lesson, during which I'll be providing an overview of the first version of the application environment, detailing its architecture, and it will introduce the concepts we'll use when we implement this in the following demo lesson. The application environment is the container within which our application sits. In the real world, the application container would likely be fairly complex. It could be a 3 or 4 tier application architecture with a web server, an app server, database servers, and potentially other infrastructure such as reverse proxies. For the purposes of this case study, our application environment is going to be simple. A web server running PHP and a simple PHP application. The application environment will use the shared services infrastructure we've created in the preceding lessons. And by now, this should be familiar. It's a dual availability zone design with logical private and public zone concepts. Currently, the shared services environment has 2 subnets, 2 public shared infrastructure subnets, which contain 1 NAT gateway each. All supporting infrastructure such as routes, elastic IPs, and an internet gateway have all been configured. This environment will be static. Its life cycle is near infinite, and we can assume it will remain in situ for as long as the application environments are required. At this point, I want to introduce another entity, and that's the application bucket. This bucket is the endpoint for the development process. As files are committed into GitHub, a build server builds code and outputs a source code bundle into the application bucket. In this case study, we're going to keep the naming simple. Each bundle will be called appx.zip, where x is the version number. Additionally, the developers are expected to produce automated testing definitions. These definitions provide details to our system of what output is expected for the particular version of the application. These files are named testx, where x is the version, and they are paired with the corresponding appx.zip with the same version. So it's at this point that our application enters the view. We start obviously with a CloudFormation template, app-environment.yaml. And this contains the definitions to create our application environment stack. And this definition can be used 1 to many times. We can have 1, 10, 100, or even more. Our template needs some inputs. First, it needs an application version, the X value. And it uses that to pull all of the required files from the application bucket. Then it needs some information from our shared services environment. Specifically, it needs the URL of the application bucket. And it uses this together with the application version to get the required application and test payloads. It also needs the VPC ID from the shared infrastructure VPC, together with the private and public route table IDs. And it needs these to allow the application environment to slot in and communicate with other elements of the shared infrastructure VPC, but more on this in a second. Lastly, it needs some external input, either from a human or an automated process. It needs the environment type, so dev, test, prod, or pre-sales, and it needs CIDR or IP ranges to use for the subnets which it creates as part of the provisioning process. So once the app template has all of these required pieces of information, it liaises with CloudFormation and initiates the stack creation process. Now again, remember that we can be creating one stack or we can be creating many stacks, so the process needs to scale. So let's go through the stack creation process. First, it begins resource creation, and because via the template parameters we have visibility of the shared infrastructure VPC, it can slot these resources into the shared infrastructure VPC and make use of the functionality it provides, so the internet gateway and the NAT gateways. Now specifically, the application environment creates a number of things. First, it creates a pair of public subnets using the IP ranges which were input as template parameters. Then, into each of these public subnets, it adds elastic load balancer instances. While there is one logical load balancer, it actually adds at least one node to each subnet, and the load balancer will be the public endpoint for our application. The template also creates 2 private subnets, which route out to the internet via the shared infrastructure VPCs. Inside one of these, it can be both, but for now it will be one, it creates an EC2 instance, which hosts the application used for this app environment stack. It's important to understand at this stage we can have one application stack or we can have multiple. Each one which is created will occupy the shared infrastructure VPC and utilize its infrastructure. But the app environment stack makes its own subnets, its own load balancer, and its own EC2 instance, and it integrates all of these with the shared infrastructure VPC. So we could have 1 or 10 or even 100 application stacks all making use of the single shared infrastructure services. I want to quickly move on to the next slide and look at what happens with the EC2 instance during provisioning, as this is also critical to understand. So let's start with our EC2 instance, which is created by the application environment template. And of course it's homed inside a subnet which is also created by that template, and both of these live within the shared infrastructure VPC. The instance finishes provisioning and we've provided it with some user data via the CloudFormation template. Step 1 of the user data runs a CFN init process against the stack, and it does this to retrieve and execute the CloudFormation metadata associated with this resource, essentially its configuration directives. The first one of these is configure CFN, which installs and configures the CFN HUP process so that the instance can react to any stack updates and update its configuration. The next step is the install www configuration key, and this installs Apache and PHP, and it ensures the former is running and set to be started up by default. Next is the config app config key, and this is the key responsible for the download and installation of the application. It uses the S3 app bucket together with the version number supplied to the stack, and uses this to retrieve the application and the test payloads from the S3 bucket. The test payload is a test file called test.pattern. Its contents consist of a test string that the app should output. Knowing this, it does a HTTP request to the application and compares them. The success or failure of this check is reported back to the stack via the create condition, and the stack creation process passes or fails as a result. And that's how the application works at a high level. It performs initial configuration, installs prerequisites, downloads, installs and configures the application payloads, and runs a comparison between what the application outputs and what it should output. If they match, the stack creation is successful. If not, it fails. Now, it's not perfect and we do have some problems, so let's look at these on the next slide. So while the solution works, there are some limitations. We have 3 fairly serious ones, which we'll look at fixing as this section continues. Firstly, as you'll see in the demo lesson, there are a lot of parameters required for the application environment template, and thus any stacks that you create with this template. You need to enter the bucket URL, VPC and subnet IDs, and many more. This means the process will need to be automated or it's prone to human errors. Secondly, the subnets used for the application environment, so the 2 public and 2 private subnets, need to be entered manually. The VPC uses a /16 address block, so there's plenty of space, but there's no way to auto-allocate IP ranges for subnets, so there needs to be some human intervention required, and this needs to be a skilled person or process, as it requires knowledge of IP addressing and IP subnetting. Lastly, while there is a check for the successful creation of a stack, and I detailed this on the previous slide, there isn't a check for when a stack update occurs, and you will see that we can perform app upgrades using CloudFormation, but after the initial create, there are no further success checks, and it's definitely a problem that we need to resolve because we need this automated testing to happen every time an application is deployed, whether that's a create or an update. Now, we're going to resolve these problems over the coming lessons, but for now, just be aware that they exist, and we'll demo them all shortly. Well, Cloud Gurus, that's the end of this theory lesson discussing the application environment. If you do have any questions on this lesson or any of the others, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next, which will be a demo lesson where we'll implement the application environment together. Hello Cloud Gurus, and welcome to the second demo lesson of the Cody's Development LLC case study. In this demo lesson, we're going to look at the application environment template, specifically how this template relates to the application environment architecture that we discussed in the last theory lesson. There are a couple of steps which I need to make sure you've done before we begin with this demo lesson. The first is that we need to go to the CloudFormation console and ensure that the shared infrastructure stack, so the shared infrastructure.yaml template that we discussed in the last demo lesson, has been applied. Next, I needed to go to the EC2 console, click on key pairs, and make sure that you've created an advanced CFN key pair, and this needs to be in the region where you're intending to apply the application environment template, and it needs to be the same region where you have the shared infrastructure template applied and the shared infrastructure stack created. The next thing is I want you to open the S3 console, and I'm going to do this now to save a little bit of time later on. We're looking for a bucket that has shared infrastructure in the name, specifically shared infrastructure -S3 app bucket and then a random string. Go ahead and make sure you've got that bucket and then open it. And this is the bucket where the application and test payloads are going to reside in. And this is as good a point as any to take us back to the lessons file folder. And we're looking for the 202 app environment version 1 folder. And this folder is either in the single zip file that you downloaded from the resources section of the A Cloud Guru website for this lesson, or it's in the larger collection of files and folders downloaded as part of the course files bundle located on the course GitHub repository. Either way, you're looking for the 202 app environment version 1 folder. So go ahead and open that. Now you'll notice within this folder, there's a lot of files and folders. We have the application environment 1 template, which is a thing that we're going to apply very shortly. But as well as that, you have 3 application folders and 3 application zips, and 3 test folders and 3 test zips. Now you'll notice, as we talked about in the theory lesson, there's always an application and a test bundle that fit together. App1 and test1 are companions and always go together. And the reason for this is these form part of our automated application and testing procedure. Now this is a very simple proof of concept demonstration. If we open up, for example, the app.php that's part of application 1, and this is contained in the app1.zip file with the same folder structure. If we open this file, we can see that all it does is output a specific piece of text. In this case, hello world, working version 1. If we look at the test.pattern that's within the test1 folder, and for this you might need to pick a specific application to open it in, we'll pick Visual Studio Code, you'll see that this is a pattern file which does a text-based pattern match against the output of the application file. In this case, the test pattern that is expected for version 1 of our code, so if we open the app.php for version 1, the test.pattern, so the pattern that's expected to be output from the application, exactly matches the text that is output from the application. And as we'll talk about in a second, what happens is we run a test to grab the output from this application and test it against this pattern. And if they match, we deem the application to be working. So version 1 of the application works correctly. Now let's look at the same for version 2. If we open app.php for version 2, we can see that it outputs hello world and then a random string and then version 2. And if we look at the test pattern for version 2, and we open this also in our Visual Studio Code editor, this time you'll see a problem. What our test pattern is expecting is hello world, working, version 2. What the application outputs is hello world, random string, version 2. And version 2 of our application is designed to flag as a failure. It illustrates what happens when the application deployment fails. So assume for 1 second that if we're deploying version 2, it's designed to simulate a bad piece of application code, a bad deployment. We can have a look at the same files for version 3, and in version 3's case, it's as expected, hello world, working, version 3, and the test.pattern matches that. So the only thing that's in app1, app2, and app3 is a folder called app1, app2, and app3, and then within that folder is always an app.php application file. And likewise, within test1 zip, test2 zip, and test3 zip, we've got a folder called test1, test2, and test3, and within that is a test.pattern file. So they're just a simple set of application files and application test bundles. And what we're going to do is we're going to upload each of them into our application bucket. So find the bucket, find the S3 console, locate the bucket, click on upload, select to add files, locate the 202 application environment version 1, and then I want you to select app1.zip, app2.zip, app3.zip, and then their companion files, test1, test2, and test3.zips. Click on OK and start upload. And all we're doing there is uploading all of these files to the application bucket, and these will be referred to as part of our application environment deployments. So just make sure you've got 6 files, 3 apps and 3 tests. Okay, so now we've got those, I want to quickly review the application environment template that we're going to be deploying. So go to the lessons file folder and open appenv1.yaml. Okay, so this is our application environment template. And the first thing that stands out should be the number of parameters that are required. We've got a VPC ID, and that refers to the shared services infrastructure VPC. We've got the public route table ID, the private route table ID, another private route table ID. We need to specify the application version that's required, the application bucket URL, the type of environment that you want to provision, so dev, test, prod, and pre-sales. We need to define an application public subnet CIDR range, and we need 1 of those for each availability zone. And then we've got a corresponding private subnet CIDR range required, again, 1 for each availability zone. And notice that almost none of these parameters, the exception being the environment parameter, almost none of these parameters have defaults. So each of these will require us to populate a value in, and generally the values are taken from the shared infrastructure VPC. Now the exceptions to this rule are the application, public and private CIDR ranges. I mentioned in the last demo lesson that subnet CIDR blocks need to be within the range used by the VPC. The problem is that each time we apply this application environment template, we need to decide on CIDR ranges for each of the subnets. They can't overlap with each other, they can't overlap with the CIDR ranges used within the VPC, and they can't overlap with any of the CIDR ranges used within any of the other instances of application environment stacks. So this is a problem. This requires some networking knowledge and coordination to be able to apply this specifically when we're applying more than one application environment at a time. This is a significant problem. We discussed this in the theory lesson. It's one of the problems that we need to mitigate as soon as possible. Now, the template does have some redeeming qualities. We use a lot of runtime enumeration for a lot of the values. So we have the mappings block here, which allows the template to adjust the AMI used depending on the region that it's being deployed in. We have an instance size mapping, which allows the template to decide on a size for the EC2 instance that's used based on the environment or the environment type that's being deployed, so dev, test, prod, and pre-sales. And we use a lot of CloudFormation functions to dynamically select availability zones throughout the template. Now, all of this should be familiar. If you haven't experienced it in your own production usage of CloudFormation, then we've definitely done it in the first case study of this course, so it should be second nature by now. What I want to draw your attention to specifically is the configuration of the EC2 instance. Now, I touched on this in the theory lesson, but what we're essentially doing in the user data component of the EC2 instance is this. We're using the function base64 because, as we've discussed elsewhere in the course, the user data directive within CloudFormation expects base64 encoded text. We're using the sub function to perform variable substitution, and we're using pipe to pass the sub function multi-line text. Now, we're updating the bootstrap utilities using the yum command, and then we're engaging the cfn init process, which downloads and runs the desired state metadata for this resource. After we've executed the desired state resource configuration, we run a global system update with yum. And here's the specific thing that we do within this case study that we didn't do as part of the last case study. In this example, we use the Linux curl command, and we curl the local web server, so the EC2 instance itself, then the application.php file. And that's our application file that we're deploying as part of the bootstrapping of this instance, and I'll show you that in a second. Once deployed, we curl that so we get its output, and then we use grep to compare that output against our test.pattern file. And that file is downloaded as part of the test.zip, so test1, 2, and 3.zip. Now, I mentioned a second ago that the application and the test bundle are a pair. The test bundle contains a test pattern that should match the output of the application PHP. And this is a really cut down, simplified version of how automated testing would work in a real development company. You have an application that you deploy, and then you have a set of automated test definitions which you check against the application. If the output matches, the test passes. If the output doesn't match, it fails. And then lastly, we run cfn signal to signal CloudFormation of a success or failure, and we send, using cfn signal, the exit code of the previous command. So if this set of commands passes, if the test.pattern and the application match, then we send a success signal to CloudFormation. If the previous command fails, so if the test pattern and the application don't match, we send a failure. And that controls whether the creation of the stack passes or fails based on whether we've got a successful application deployment or not. So let's quickly look at the CloudFormation init directives and familiarize ourselves with what we expect to happen. The first config key is configure cfn, and this is the same as we used in the WordPress incorporated case study. So all we're doing on this one is we're installing the cfn hup utilities, we're making sure that the cfn hup utility is started and that it's started on boot. In other words, we're making sure that this CloudFormation stack can react to changes to this metadata. So once configure cfn has completed, then we run the second config key, which is install www. And install www installs the HTTP server, it installs PHP, and it makes sure that the web server is configured to start on boot and that it's running after the completion of these configuration directives. So essentially it installs Apache web server and PHP, and it makes sure Apache is set to start on boot and that it started when this completes, so when these configuration directives complete. And then we have the config app configuration key, and this serves two purposes. The first is that it downloads the application zip file, the specific version of that file that we specify in the parameters. Secondly, it downloads the test.pattern file, again from our application bucket, and it uses the version that we specify as a parameter, and unzips that pattern file into the desired location, which is var www.html. And those are the two assets that are used as part of our check, this curl statement. So it curls the web server, grabs the output of the application file, which is downloaded here, and then the output of the application is compared against what's in the test.pattern file, and the test.pattern file is downloaded here. Now I want to stress that this is a super simple example of an automated testing process. You could go away with the theory and practice that you've gained in this demo lesson and the previous theory lesson and implement something much more complicated. But at a foundation, they will all share the same architecture. You download some assets, you download and install some method of running some tests, and then you run the test on the assets. Our example is super simple. It uses one PHP file, one test file, and the curl utility. But these concepts can be extended to something that's much more complex. The key learning objective is that you're using this architecture to influence the success or failure of the stack at stack creation time. So that's it with the template review from a code perspective. Let's return to the AWS console and we'll implement this template together. And specifically, I want to spend some time talking about how the template looks and how complex the parameters are to populate. So let's flip back to the AWS console. Well, thanks for listening, Cloud Gurus, and this is the end of part 1 of this lesson. If you do have any questions, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to finish this part and continue with part 2. Hello Cloud Gurus and welcome to part 2 of this lesson. This part continues immediately from where part 1 left off, so let's jump into it and get started straight away. So go to CloudFormation, click on Create Stack, upload template to Amazon S3, and pick app.env1.yaml, which is version 1 of the application environment. Click on Next, and straight away we can see that the number of parameters that we need to populate is going to be an ongoing problem. I'm going to start by naming the stack and I'm going to call it Application Environment 1. Next, I'm going to need the VPC ID, the public and private route tables, and the application bucket URL. And I'll get all of those from the shared infrastructure stack. So if I open stacks in a new tab, highlight shared infrastructure and click on outputs. First value I need is the VPC ID of the shared infrastructure stack. So copy that and paste it into the VPC ID parameter box. Then I need the public route table ID. Make sure you get these correct. So this is public route table. Paste that in. Next, I need the private route table A, which is the top one here. These might be in a different order on your screen, and they will be specific to your environment. So make sure you enter the ones of your shared infrastructure stack, not the ones I'm using. So copy private route table A, and then do the same for private route table B. And then you'll need the application bucket URL. And this is this one. So copy that whole text, make sure you get it all, and paste that in. Now we'll leave the environment type as dev, and we're going to enter 1 for the application version. So this is a version that we know works, so version 1. Now this is the major problem with this application environment template. We need to have some knowledge of IP addressing in order to be able to complete these values. In addition to that, we also need to know if any values are being used by any other application environment templates because we can't have overlap. Now as luck would have it, we're in complete control of this environment, and we don't have any other application environment templates to worry about. So the only thing we do need to worry about are the subnets that are used within our existing VPC. So let's just return to our AWS Management Console and go down to VPC and let's open that in another tab. If we click on subnets, and if we sort these subnets by the CIDR range, we can see that we've got our 2 subnets here that form part of this VPC. So they're using 10.20.0.0 and 10.20.4.0. Now this means that in our VPC so far, because these are /22 ranges, that we're using 10.20.0.0 to 10.23.255, and then we're using 10.24.0 to 10.27.255. So the first available IP range that we've got to use is 10.20.8.0. Now that will be the same in your environment, assuming you've not changed any of the defaults, which you shouldn't have. So just remember 10.20.8.0. And then let's go back to the create new stack screen. Now this is where it gets slightly complicated. This is the point where we need to define the CIDR blocks that our application environment subnets use. I'm going to keep things simple and I'm going to use /24 or class C IP address ranges here, and I'm going to do it because it makes it a lot easier to decide upon these values. We know that the first available IP address is 10.20.8.0. And if we define this as a /24 IP address range, what that means is that the next available range after that will be 9.0, because a /24 range always increments the third octet by 1. And likewise, the next range will be 10.20.10.0, and the next range after that will be 10.20.11.0. And so by using /24 ranges, it makes this a bit simpler to do while this is a manual entry situation. So pick 10.20.80/24, 10.20.90/24, 10.20.10.0/24, and 10.20.11.0/24. And at this point, we've entered all the required information. So we've got the application bucket, we've got the CIDR ranges for our application subnets, we've got our application version number, so version 1. We've left the environment at dev, which is the default. We've entered route table IDs for both private route tables, so A and B. And likewise, we've entered one for the public route table. And finally, the VPC ID. So I want to stress at this point, just consider how difficult it is and how time consuming it is to both manually enter all of these parameters, and how the knowledge available to update these parameters, so the application CIDR blocks, might not be available every time you want to deploy this template. And even if they are available, it's not something that's super quick to do. Somebody needs to sit down and consider which IP addresses to use at this point. While it's easy for me as part of this demo to give you the values to use, it's not trivial to do this if you're in an environment where you might have 10 or 20 application environments, which is a total of anywhere between 40 and 80 individual subnets. You'll need to keep track of the subnet allocation for each application environment, both when they're created, when they're active, and when they're removed. When they're removed, you need to deallocate that range and use it for something else. So both the lack of automation and the skill set required to be able to populate some of these parameters poses as a significant challenge. So let's go ahead and apply this. Let's click on Next. We don't need to populate any of these options, so Next again. And just review the information, make sure these subnets are correct, 80, 90, 10, 11, all 24s. Make sure that these route table IDs match your environment. If there are any errors at this point, specifically with these values, the template will error. And again, if there are any problems with these values, your template will also error. So keep that in mind. Once you're sure it's all good, click on Create. And the application environment will begin its instantiation process. Now this might take between 5 and 15 minutes to create. So I'm going to go ahead and pause the video until we have a change in status. You might want to utilize this time either to watch the event log so that you can understand what the stack's actually doing, or alternatively, you can go and grab a drink or some food and wait for this to complete. Either way, I'll pause the video and I'll resume it shortly once we've got some progress. Okay, so our application environment version 1 has completed. And if we click on outputs, we can see that we've got an endpoint output, and this is an elastic load balancer. So this is a load balancer that's sitting in front of our EC2 instance, and it's providing access to our application. So if we go ahead and click on that, because it's version 1, we should see hello world working version 1, and that's the actual string that our application outputs. Now if you do this in your environment and you get a DNS error such as DNS name not found, just give it a couple of minutes. It does sometimes take a short while for the load balancer's DNS name to register in DNS, and so that you can click on that link and see it. So if it does fail, just give it a couple of seconds and then try again. So we can see the application worked. It's all been a success. We've made the EC2 instance, we've bootstrapped it, we've deployed the application, we've deployed the test payload, and if we click on events, we can verify here that CloudFormation received a success signal from our EC2 instance, so from unique ID I and then our instance ID. And that means that our automated test, so our curl of the Apache web server, and then our compare with the output of our application to our test.pattern content using the grep application, we can see that that's a complete success because we've received this success signal. Now we can verify that. We could actually connect to this EC2 instance and just have a look and see what's happened. So why don't we go ahead and do that? Let's click on Resources and click on EC2. And we can see our EC2 instance. And if we right click and put connect, we can see the connection string that we need to enter into our terminal to open a session to our EC2 instance. So let's go ahead and copy that and then open terminal. And you need to go to the location where you've downloaded the advanced CFN PEM key that you either made earlier in this lesson or in the last section of this course. Whenever you made the advanced CFM PEM file, you need to locate that file now and you need to be in that folder. So for me, it's the downloads folder. See there, advanced CFM.pem. If I paste in this connection string and press enter, accept the identification warning, and that'll take me to my EC2 instance. And then let's clear the screen to make it a bit easier to see. And we could go to /var www HTML, and we can see that the bootstrapping has downloaded both the app.php and the test.pan. So if I run a cat on the app.php, we can see that it outputs the Hello World working version 1. And likewise, if I cat the contents of test.pan, which is used to actually compare, we can see also Hello World working version 1. And that's how our automated testing process works. And if we clear the screen again and go to /var/log, we'll be able to see our cfn init.log and our cfn init command.log. And we can open either of these files, and these will contain the output of the desired state configuration steps, so the cfn init steps. And if we go to the bottom of the file, it shows signaling resource EC2 in stack application environment with this unique ID and status success. So our end-to-end bootstrapping, deployment, and testing process was a complete success. Thanks for listening, Cloud Gurus, and this is the end of part 2 of this lesson. If you do have any questions, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this part and move on to the next. Hello, Cloud Gurus, and welcome to part 3 of this lesson. And this continues immediately from the end of part 2. Let's get started straight away. So there's 2 more things I want to demonstrate with this version of the application environment template. The first thing is to make sure you're in the /var/log folder. And I want you to maintain a tail on this command. So I want you to check the output for the cfn hub command. So what we're going to do is tail-f, and tail-f just ensures that we keep a monitor on this file. So we make sure that if we change anything on the system and it updates this file, that we see the output immediately. So do a tail-f cfn-hub.log. Now my current local time is 15:30. This server is obviously running in US East 1, and so its local time is currently 5:30 AM, so 05:30 AM. Now we know that the default time to check for any changes in resource metadata based on CFN Hub is 5 minutes. And we covered that during the last section of the course, during the WordPress Hosting Incorporated lesson, where we talked about CFN init. We know that the CFN Hub process listens for changes in the CFN metadata. If we make any changes to that metadata, it detects those changes and runs a command of our choosing. And in this case, it's the cfn init command. So if we go back to the template and scroll down, we've got the configuration for the cfn auto-reloader conf file, and we direct triggers equal post update, which states that run this if any stack updates occur against this path. So if this data changes and if it's updated, then run this action, and the action is cfn init. So essentially, if any details on the metadata of this EC2 instance change, then run cfn init. And what that does, if we go back to the CloudFormation console, is we can right-click on the application environment 1 and click Update Stack, leave the current template in place, and change the application version from 1 to 3. And we know that 3 is another working version of our application. So let's click Next, Next again, and click on Update. Now, ticking the Outputs box, we can open the endpoint for this installation. So we can see Hello World working version 1. Once this stack update has completed, we will expect to see Hello World working version 3, because the application, or version 3 of the application, will correspondingly print version 3 as its output. So let's give this a couple of seconds to update. I'm going to pause the video until this is completed, and if you're following this along in your own environment, then just keep an eye on the event log. It shouldn't take too long to complete this process, but I'm going to pause the video and resume once it is complete. So this is completed now. It only took about 3 or 4 minutes. If we refresh, we can see update complete. And let's go back to the tab where we've got the output of the application and hit refresh. And this is interesting. It still says version 1. And the reason for this is because the CFN HUP process refreshes every 5 minutes. The last time it did a check for the metadata was at 05:43, which is approximately 4 minutes ago. Now what we'll expect is that this should update. The CFN HUP process should do a scan of the EC2 resource, so the metadata of the EC2 resource. It should identify that there was a change. Once it identifies the change, it should spawn the CFN init process, which will rerun the configuration directives, perform a download of the test data and the application file, and we should see that when we refresh, it's an updated version. So any second now, we'll expect to see an update in this log file. And just for reference, this is the CFN HUP log file in varlog. At 05:48, it's detected data change from previous state, and its action CFN auto reloader-hook will be run, and that's run the action we specified in this configuration file. And returning to our CloudFormation template, this is the action, CFN init, and then the relevant configuration options. And what this has done is rerun CFN init with these new configuration directives. So if we refresh this, we'll see that it's now running version 3. So that's working as intended. We know we can change a parameter on a CloudFormation stack that influences the EC2 resource. This change is detected by CFN HUP, which reruns the CFN init process, that reruns the configuration directives, downloads the new version of our application, and we can see the output of that application in our endpoint when we do a refresh. So one final thing. Right-click on this stack again and put Update Stack. Click on Next. But this time, I want the application version changing from 3 to 2. Now, version 2 is the failed version of our application. It's the version where the output from the app.php is different than the one expected by test.pattern. So logically enough, you'd expect this update to fail. So let's click on Next, 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 and Update. And we'll allow the stack update process to complete. Once this is complete, we'll need to wait 3 or 4 minutes for CFN HUP to detect the change, rerun CFN init, re-download version 2 of the application file and the test.pattern file, and then we'll be able to see what the status of the stack is and what the output of the application is. So this should only take a couple of minutes to do the stack update. It needs to update the metadata of the EC2 instance, so that shouldn't take too long. Let's just keep clicking on refresh, and the update's complete. So let's refresh it. We can still see we're on version 3, and that's because CFN HUP has not had a chance to detect the change in the metadata for the EC2 resource yet. So let's go back to our terminal, and the last poll occurred at 05:48, which by local time was 4 minutes ago. So any second now, we'd expect a new line in the CFN HUP log file, and it should inform us that data has changed from the previous state and that it's running the action for CFN auto reloader-hook, which is a rerun of CFN init. So let's give that a couple of seconds to complete. Once that has, we'll refresh the tab that's got our application output in and see if any changes occurred. Should be happening any second now. And there we go, data change has been detected. Let's return to the console and do a refresh. And we can see, hello world, random string version 2. But that has highlighted an interesting problem. The stack is showing us update complete. Our application has definitely updated to the problematic version 2 update, but we've got no errors. And we've got no errors because we've got an inherent problem with this version of the application environment. The testing routine only works once at the time of stack creation. If we were to create another stack, but this time use version 2 of the application, we would get a stack create failed message because the check, the automated check, is only run once when the stack's created. So if we do create a stack directly with version 2, that will be a problem. Now, I'm not going to go into detail why at this stage we have a problem with the automated test, as that is the subject of a follow-up lesson. For now, just be aware that creation policies only run once, that is when the stack is created. Because we're using the creation policy mechanic to do our test, we only get the option of running the test once when the stack's created. Now, I'll demonstrate there are ways around this, and as I mentioned a second ago, that is the subject of an upcoming lesson. For now, that's the end of this demo lesson. I hope it's been useful, and I hope it's demonstrated at a simple level how we can incorporate automated testing processes within our CloudFormation templates. And I hope it's also demonstrated a number of fairly significant problems that we have with our application environment. One, that there are a large number of parameters that we need to enter when creating the stack. Two, that some of those values require networking knowledge and advanced knowledge of the current state of the environment. So for example, we know the subnets can't overlap those in the VPC, and we know that they can't overlap each other, nor can they overlap subnets from other application environments. So that awareness requirement represents a problem. And finally, of course, there's the issue with the automated testing, the fact that it only works once when we create the stack. What we're going to do over the duration of this section of the course is enhance this template, so evolve this template to resolve a number of these major issues. And we're trying to progress to the point where we can implement the application environment template in an automated fashion, either with human interaction or using an automated provisioning system. So you can go ahead and delete the application environment one stack at this point. We're not going to be using it anymore. And you can either delete the shared infrastructure stack, or you can leave it in place if you're going to be using it in an upcoming lesson. It does carry a cost. It is running 2 NAT instances within this stack. So if you're not going to be doing any lessons for a day or 2, you might save a little bit of money by deleting this stack and recreating it. But equally, you're fine leaving it in place. And we will be using the shared infrastructure stack in almost every lesson in this section. Well, thanks for listening, Cloud Gurus, and that's the end of this lesson, where I've given an overview and demonstrated the implementation of the application environment stack. If you do have any questions on this lesson or any others, then please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello, Cloud Gurus, and welcome to this lesson, where I'm going to introduce AWS-specific parameter types. These parameters offer enhanced functionality versus the generic alternatives such as string. Let's get right into it and see them in action. By now, you should be familiar with CloudFormation at a fairly good level, and have used basic parameters extensively, both within this course and within your own environments. You should know that we have 4 types of basic parameters. We've got strings and we've got number, and they're scalar data types, which mean they accept a single value, either a single long string or a single long number. And then we have number lists and we have comma delimited lists, and both of which allow entry of comma separated values, floats and integers in the first case, and strings in the latter. What all of these parameter types have in common is that they're dumb, they're generic, they don't carry any CloudFormation specific intelligence. In this example, we've got 2 parameters. One's a simple string and one's a comma delimited list, neither allowing anything beyond basic text entry. They are base level dumb parameters. We use them because they're the most flexible types and they accept the widest range of values, even values which are incorrect. In this example, I could proceed to create my task with the values shown on screen, even though they're clearly generic incorrect values. I could add some constraints, as discussed earlier, to ensure the format is correct, but there's no way, as things stand, to allow only correct inputs from an AWS system perspective. There's no way with CloudFormation, as we know so far, to vet input from a validity perspective. Let's move on and we'll look at how we can add the ability for CloudFormation to perform some pre-validation. CloudFormation offers a number of specifically targeted parameter types, types which instruct CloudFormation that the data being entered relates to specific objects or types of objects within the AWS platform. Before we look at those, all of the AWS data types are divided into 2 families, lists and scalar types. This should be logical by now. Scalars are used when the desired input is a single value, and lists are used when multiple values are optimal. From a CloudFormation perspective, scalar types resolve to base strings, i.e. a VPC ID, whereas lists where multiple things can be entered resolve to lists or arrays within CloudFormation. Even if a single value is entered into a list type, it's a list with 1 element, and this is important to understand. So what specific CloudFormation data types do we have? Let's run through some common examples. This list isn't exhaustive, but I'll make sure the list which is shown on screen now is where you can have a look at the full set within the AWS documentation. First, we have this data type, and this will present a list of the VPCs or VPC IDs in the current region of the current account. When viewing it through the console UI, it looks like this. It enhances a traditional string entry dialog by adding a suggested drop-down containing valid entries. You can click a VPC in the drop-down to populate the box, and you can also start typing an ID or a name tag, and the list will adjust the drop-down with suggestions. Again, remember the end result from CloudFormation's perspective is just a string. It's just a VPC ID, just like it would be if you were entering into a normal string field. The difference here is that you're performing layer validation before continuing. Next, we have availability zone name, and just like the VPC ID, will allow the selection of an AZ within the region the stack is being applied in. And this can be useful when you have certain single AZ resources which require some level of user input. Again, it performs pre-validation. I'm going to keep stressing that point. It's really important, as we'll see later in this lesson, the pre-validation concept. Next, we have key pair / key name, and this functionality is very similar to the above two types, but it allows me to illustrate one of the reasons that these custom types are powerful. Consider a template where you're provisioning some AWS resources, including an EC2 instance. Your template has a normal string field asking for a key pair name. So you create the stack, you enter the template parameters, but let's say you did an incorrect key name. CloudFormation provisions the resources, starting with, say, an S3 bucket and an RDS instance, and then it starts provisioning the EC2 instance. And then it fails due to an invalid key. The whole process might have taken 5 to 10 minutes simply because of a bad parameter value. If you entered a key which doesn't exist, you'd have to wait 5 or 10 minutes until the process failed. Now consider the flow when using the AWS specific key pair type. The create stack is the same as before, as is the parameter entry stage, but unlike generic data types, the user is presented with an invalid key message if there are key issues before the resources are created. You've optimized the flow of your stack creation process by capturing the issues earlier in the process. No time or money is wasted by beginning resource creation until the parameter values have been pre-validated. So to reiterate, in this case, you've gone from a process where you enter an incorrect key name and waste 5 to 10 minutes of time before you're warned, to using a data type which validates that the key exists before the resources are even initiated. So you get that feedback, that instant validation that the key is not valid or it is valid straight away. You don't have to start creating resources. Now, as well as scalar AWS specific types, we also have lists. Lists use the basic concepts as the scalar types, but the intention is to allow selection of one or more elements. First, we have the subnet ID list, and this, as the name suggests, allows the selection of a list of subnets. It's presented in the UI like this, and it resolves to an array or list of strings, in this case, a list of subnet IDs. Now, this type might be commonly used when you're setting up an auto-scaling group, where you want to direct AWS to create the auto-scaling groups with a certain set of subnets as members. Now, we also have the list of availability zones, the list of instance IDs, and the list of security group IDs, and they all follow the same logic. They present a list, allow searching, and offer some pre-validation. All have their possible uses. Instance ID lists, for example, might be used when you're creating a static elastic load balancer, and a static elastic load balancer is one which isn't linked to an auto-scaling group. And this data type will allow you to select the instances which you want to add to the load balancer, and again, it pre-validates these, so you can't add instances that aren't valid. Okay, Cloud Gurus, that's the end of this brief lesson on AWS custom parameter types. I hope it's been useful, and I hope I've got across just how powerful these parameter types are, and how the pre-validation performed by them is incredibly useful and can potentially save a lot of time and money. If you do have any questions on this lesson or any others, then please do reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus, and welcome to this demo lesson where we're going to look at CloudFormation custom parameter types. Additionally, we're going to look at some other template changes that we can make to improve the user experience of parameter entry, specifically within the console. So let's get started, and the first things that I'll need is you'll need to be logged in to the CloudFormation console that you're using for this course, and secondly, you'll need the resources for this lesson. And you'll have those either because you've downloaded this lesson's resources from the resources section of the Cloud Guru website, or if you've downloaded the course files from the course GitHub repo. Either way, you're looking for the 203 AWS parameter types folder. So go ahead and open that. Now, this is not going to be a technical demonstration lesson. I've got 4 different versions of the application environment template, and I want to step through some of the changes that I've made to each of these templates and just look on screen as to how each of these templates slightly alters the ease of entering parameters and the user experience of doing so. So let's get started with application v1.yaml, and I'm going to straight away start applying this in CloudFormation. We're not going to actually apply it and let it create a stack, but we're going to load it into the system and see how it looks. So create a new stack, upload the template to S3 and choose a file. Make sure we have the correct lesson file folder selected, which is 203 parameter types, and pick the application environment 1.yaml. So go ahead and select this and click next. And this should be a familiar site. We've got the stack name entry box, which is always going to exist. And then we've got a large number of parameters. And at this stage, they're all standard string entry fields. So there's no intelligence. If we select the VPC ID box and type a value, there's no intelligence whatsoever. It's just a straight string text entry box. And in addition, all of these are sorted alphabetically, and they're using their logical resource name, so logical parameter name values that are defined in the template. If we go ahead and open the template, so version 1 of the template, you can see the corresponding area where each of these templates is defined. So you'll see we've got them in uppercase, and they match the parameters that we've just seen on the previous screen. And the description that we've picked for each of these parameters, we can also see next to the entry box on the parameter screen. So nothing should be new. This should be basic CloudFormation technology. You should be used to using this both in this course and within production environments that you might be involved with. So let's click on cancel. So then go back to the lessons file folder, and I want to draw your attention to application environment 2A. And this is the first revision that I've made as part of this lesson. So let's go ahead and open this template. And it'll be nice and quick to explain the difference. The only difference is that the VPC ID parameter has changed from being a string type to an AWS custom type. So AWS EC2 VPC ID. That's the only change. It's a nice and simple one. And if we go back to the CloudFormation console and we attempt to apply this template, so again, upload to S3, choose the template and pick 2A, and then click on next, and we're taken back to the parameter screen. And it looks very similar, apart from the dumb text entry box, so the standard string parameter type entry box, that's been replaced by a drop-down. And if we click on the drop-down, we can see a list of all of the VPCs within this region within our account. There's no scope for misentry. You can select a box and that value will be propagated into the box. Or alternatively, you can start typing a VPC ID and you'll be presented with an auto selection or auto completion style dialog. If you've got multiple VPCs, this will be much more useful, but you can start typing the ID, and as you type specific characters, it will filter out those VPCs which don't apply, leave the ones that do apply in the box, and allow you to click to select. So this straight away improves the parameter method. You can't enter incorrect parameters. You end up with a selection, you select one, and it's populated into this parameter box. Now, however this looks on screen, it translates within the CloudFormation template to a simple string. So if we go back to the template, we can still refer to this in the same way using the !ref shorthand function type, and actually refer to the string version of whatever we've entered in that dropdown. So it doesn't change the functionality of our CloudFormation template, it just improves the user experience and reduces the chance of errors. Now in this case, there's only the one parameter value, so VPC ID, that seems to fit the use of a custom parameter type. All the rest don't. All the rest are asking for information that isn't appropriate when we're using a custom resource type. But I do have a number of other things that I want to show you. So go back to the lesson files folder and open application environment 2B. Now you'll notice straight away that there's a whole new section to this CloudFormation template, the metadata section. Within metadata, we're defining AWS CloudFormation interface. And this allows us to influence the way in which CloudFormation presents the parameters to us. We define a key called parameter groups, and the value of this key is a list. And this list is a list of parameter groups. And a parameter group is this, so this list element, this, and finally this one. So by creating three different parameter groups, so we've got the shared infrastructure parameter group, the application environment networking parameter group, and the application environment configuration parameter group. And in each of these groups, we've got a key called parameters, and then a list of the actual parameter logical resource IDs that we want to be in this group. So for example, in this case, we've got one called shared infrastructure details, and we're saying we want the VPC ID, public route table, private route table A, private route table B, and application bucket URL parameters to be part of this group. So take a moment to familiarize yourself with the syntax that this uses. So we've got parameter groups key whose value is a list, and then each element of that list is a parameter group block, and that has a label, and it has the parameters which are part of that group. And if we go back to the CloudFormation console and cancel the previous screen if needed, go on create stack, upload a template to S3, and if we pick version 2B and then click on next, you'll see that the interface presented is completely different. Now we have parameter groups. So we have shared infrastructure details, application environment networking, and application environment configuration. And notice that these are no longer in alphabetical order within this group. What we can do is we can define our own specific order. In this case, I've directed CloudFormation to use the application bucket URL as the last parameter in this parameter group. And rather than sort that alphabetically, it's gone ahead and obeyed that directive and left that for last. So this is very much a vanity feature. It's not really a core piece of CloudFormation functionality, but it's very useful if you're anticipating that you'll need users, i.e. non-automated processes, to interact with CloudFormation, and it offers a way to tidy up the interface around parameter entry. So the last thing I want to draw your attention to is how we're using the resource ID here, so the logical resource ID. We have VPC ID, public route table, private route table, application bucket URL, and so on. And if you look at the names here, they directly map onto the resource ID, the logical resource ID values, so the parameter names in the actual template itself. So we don't have flexibility to actually look at those and refer to those with different names. So we're actually referring in our UI directly to our parameter names. The next template offers us a way to change that slightly. So let's open 2C. And if we scroll down, we can see that I've added a key here called parameter labels. So this is defined at the same level as the parameter groups key. So it's not within a particular parameter group, it's global. We're saying parameter labels, and for the logical resource ID, so the name of the parameter VPC ID, we want to call this VPC to deploy into. And if we go to our console and look at that, so note here, this is labeled VPC ID. If we cancel this, create a new stack, upload the template to S3, choose file, and finally pick 2C, click on open, and next, and pay attention to how the VPC box looks. This time, we're not using the logical resource ID. We're using our parameter label. So we're saying VPC to deploy into. So parameter labels offer us a way to introduce a more user-friendly way of referencing parameters. So rather than using VPC ID, we're using this text string, which is VPC to deploy into. And you can basically use parameter labels in conjunction with descriptions to, again, slightly improve the experience that a user may have entering parameters. It just makes everything look a bit more tidy. You can see that by using a parameter label, it also moves where the description's stored. So rather than the description being at the side, the description's stored below the parameter entry box. So again, you can adjust the way that CloudFormation is presenting the parameter entry screen. Okay, Cloud Guru, so that's the end of this very brief and slightly non-technical lesson around AWS custom parameter types, and then the CloudFormation interface section of CloudFormation templates. And I've demoed how we can use that to improve the presentation of parameter entry within CloudFormation templates. I hope it has been useful, and if you've got any questions about this lesson or any of the others, then please do reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus, and welcome to this lesson where we're going to be talking about stack reuse within CloudFormation. I mentioned in a previous lesson that we had three main problems with our application stack template. Namely, the amount of information that has to be manually entered via template parameters, which links to resources in the shared infrastructure stack. Then, that the user has to calculate and enter subnet IP ranges for the application environment subnets. And lastly, that the application tests only apply when the template is initially applied and the stack created. Updates to the stack aren't retested with the same automated testing. During the remainder of this section, we'll look at how advanced CloudFormation features can be utilized to mitigate or remove some of these problems entirely. In this lesson specifically, we'll focus on the first point. And we'll tackle this first because our application template looks like this when it's being applied. It requires somebody of a senior skill level to apply, and we need to make that easier, or improve our chance to automate it. Specifically, we're looking to find some way of removing the user interaction requirement for the following parameters. The ones which aren't highlighted are either appropriate, that they always remain manual parameters, for example, the environment type or the app version, or they're ones we're going to tackle later in this section, for example, the subnetting information. So we're going to look at the pink highlighted parameters during this lesson. So I want to spend some time talking about reuse within CloudFormation, both stack reuse and general reuse. There are 4 reuse architectures available when using CloudFormation. At least I find it useful to think of them as 4. The first 2 are user-driven methods, and the other 2 are platform or technology-driven. Firstly, we have snippet reuse, and this is a fairly basic process where resources specific to your business are added to a template library. And this template library might be in the form of a GitHub or other source code repository. Engineers within your business define resources once, i.e. the skeleton for a secured S3 bucket. And that template is added to your library and then reused by the rest of the engineers in the business on all of their projects. So there's nothing special about this process. Code reuse should be a common and well understood practice with most software development teams. All we're doing in this case is introducing it into infrastructure teams. Next up, we have an extension of this, template reuse. And this is similar to the above practice, but instead of template snippets or segments, whole templates are reused across the business. Imagine you have a template for a WordPress environment, so an EC2 instance plus Apache plus PHP, MySQL or RDS. If this is a common application stack scenario across your business, it makes sense to have one secure template stored within a source code repository. And then you can direct business teams to use that template across the company rather than investing the time to develop the template each time in separate areas of the business. So they are the user-driven practices or processes. Nothing specific to CloudFormation, but by adopting them, it will help you achieve a better value from CloudFormation. You'll be able to reuse the investment that others have put into the platform. It's worth pointing out that it doesn't have to be limited to internal reuse. There are many places on the web where templates or template segments can be reviewed, downloaded, and reused. It makes sense to evaluate pre-created works before doing something specific to your business. Chances are it's been done before. So let's move on to CloudFormation specific features which support template reuse. And first we have stack or template nesting. Consider the following scenario. Cody's development is working on a major app release. The app brings with it the ability to select the database that the product uses. Currently, this future app version consists of a load balancer, an application server, infrastructure components such as subnets and security groups, and the database. And the template is obviously fairly large and complex because it stores all of those components within it. If the business wants to have a new template with a new version of the database, for example, it needs a new template. But notice that we have many shared elements within the templates, pretty much everything but the database. What we can do in this instance is move the shared resources into a dedicated template. For now, let's call this the application front-end template. And we can use this template from within our other templates. And these other templates would only contain 2 resources. The component that is different between the templates, so in this case, the database, and the application front-end template defined as a nested resource. So what benefits does this provide? Well, firstly, the database template, i.e. the template which contains the database and the nested stack resource, they're much smaller. They only contain 2 resources. The database, as in the specific database being used, and the nested stack. So they're far easier to maintain. It becomes easier to produce specialized templates for different databases and have them as a selected option when deploying our application. When deploying the app, we would deploy these templates. They would create the database and then create the shared resources in the application front-end stack. The other benefit is that by separating the database out, it means that the application front-end template can be used on its own without the database stack. For example, with versions of the application that don't need database functionality, or where the database functionality will be hosted from the application server itself, for example, small instances or demos. Now we can still customize the deployment when we create the custom database stack. It will create the database, and then it will deploy the nested stack. Our DB stack, and let's refer to this as the parent or master stack, can provide inputs in the form of parameter values to the child or nested stack, and in some cases it has to. Any parameters on the nested stack which don't have defaults will have to be supplied by the parent stack, or the process will fail. For parameters in the child stack with defaults, the parent stack can either supply some, which will overwrite the defaults, or omit that parameter, which will cause the defaults to be used. Once the child stack has finished creating, any outputs it generates will be available for use within the parent stack via the get attribute function. So how do we actually use this in practice? It's easy. The parent stack would contain a resource, and that resource would point at the nested stack template. We use a CloudFormation stack type, and in the properties, we provide a timeout in minutes for the creation of the child stack. We give the URL to the template of the child stack and the parameters block to provide any parameters to the child stack. And remember, for any parameters without defaults, this is mandatory. Once the child stack is finished, we can access its data via outputs. And this is done, as previously mentioned, using the get attribute function. But stack nesting is of no use to us within the context of this case study. Stack nesting won't work for us in this use case. Stack nesting relies on the application of a parent stack, which creates some resources and then creates a child stack. In our case, we have two stacks. We have the application stack and the shared infrastructure stack. And although the application stack relies on shared infrastructure, we don't want a new shared infrastructure stack to be created each time we apply an application stack. Doing so would be inefficient and fairly uneconomical from a financial perspective. So what other options do we have? Let's go to the next slide and have a look. The last reuse approach that I want to talk about is cross-stack referencing. And this is a capability which was recently added to CloudFormation, or at least recently at the time of producing this course. The premise is simple enough. Let's say we have one stack, the shared infrastructure stack. And within this stack, we have a few major sections. We have parameters, mappings, conditions, resources, and outputs. Normally, all of those elements are scoped to the stack. They can't be referenced or interacted with by other stacks, unless, shown on the last slide, we use a nested stack architecture. Now we've determined that we can't use a nested stack architecture because we want to reuse the shared infrastructure stack for every single application stack that we create. We don't want an interdependency between the two, so we don't want it that every time you create an application stack, it makes its own shared infrastructure stack, and that's the way that stack nesting works. Cross-stack referencing introduced a new concept to CloudFormation templates and stacks called an export. And an export is an option set within a specific value in the output section of a template. So the value in the output section can become an export, or more specifically, the value of an output can be exported under a specific export name. Now exports have limits. Firstly, the name of an export has to be unique within your account in that region. When you reference an export, you do so by name, not by using the stack. So it makes sense that it needs to be unique in that region in your account, since CloudFormation is a region-based service. And related to this, you can't reference stack exports across region boundaries. And again, makes complete sense because CloudFormation is a region-based service. Now you can't delete a stack, in this case the shared infrastructure stack, if another stack references an export on this stack. So if we export an output value on the shared infrastructure stack, we can't delete that stack if one of our application environments utilize that export. And you can't modify or remove an output that is referenced using its export from that stack. So if we're using an export in another stack, you can't modify or change the export on the original stack. It's not possible to do. We'll look at how this works technically on the next slide. For now, we're just looking at the high-level architecture. Now, that's all that's required at the source side, that you indicate on a specific output value on a stack that you want it to be an export. Across all the stacks you may have in a specific region, you will have a collection of uniquely named exports. Now, at the destination or the consumption side, we have our application environment stack. The existing version of our stack has a collection of parameters. Now, rather than using parameters which need either default values or some user interaction, we can import the exports within our account, using them in place of other values in our template, and in this way we avoid the need to use one or more parameters. So just to repeat that, in our application environment, rather than using parameters or explicit values elsewhere within our template, we can import exported values from other stacks. And that reduces the number of parameters we need to use and improves how much automation we can achieve between these different stacks. Let's look at the code that allows this to happen. We start with our shared infrastructure template, specifically the output section. In the output section, we add an export key, which contains a child key value pair, name and the export name as the value. Then, in our application environment template, rather than referencing a parameter of that template like we currently do, we can use the import value function. And passed to that function is the unique export value name, in this case, shared infrastructure VPC. And this references that value exported in the original template. So you can see that we use the import value function. It's using the unique name, so the unique name in your region, which is shared infrastructure VPC. And rather than using a parameter for that VPC ID, we're using import value and referencing the output, i.e. the VPC ID of the shared infrastructure template. So you can see that's how it works on screen now. In the next demo lesson, we're going to use this feature to update the shared infrastructure template and stack, and we're going to set it to export all of the useful values that we might need to import and utilize within our application environment template. We're going to update the application environment template to import those exported values and avoid the need for many of the current template parameters. That's it for this lesson, Cloud Gurus. Thanks for listening, and I hope it was useful. If you do have any questions on this lesson or any of the others, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next, which will be a demo lesson where we'll implement the various technologies discussed in the recent slides. Hello Cloud Gurus, and welcome to this demo lesson. And in this demo lesson, we're going to look at the technical elements of stack reuse. Now in the theory lesson, I've detailed the architecture of stack reuse and how it's accomplished with both exports from stacks and imports into other stacks. And in this lesson, we're going to look at how that's technically implemented. Now as usual, I need you to be logged into an admin user on the AWS account that you're using for this training. And I've already done that on my system to save some time. Secondly, you need to have downloaded the resources for this lesson. And you could have done that either from the resources section of the A Cloud Guru website for this lesson, or if you've downloaded them all, from the GitHub repository for this course. Either way, you need the 204 cross-stack references folder. So go ahead and open that. And you should see a total of 8 files when you're performing this lesson. You should have 4 files that are in the YAML format and 4 files that are in the JSON format. And whichever format you pick, there should be 2 shared infrastructure templates and 2 application environment templates. One which is the version from the previous lesson, and one which is a version that's been enhanced for this lesson, taking advantage of cross-stack references. Now, as I've already mentioned, utilizing cross-stack references is a 2-part process. On the source template or source stack, we need to export some outputs. And then on the consuming stack or the destination stack, we need to import and utilize those values. So let's start with the source end of the equation. Let's have a look at the shared infrastructure stack. Now, if you're performing this within your own environment, feel free to open the existing version, which is sharedinfrastructure.yaml, and the new version. For this demonstration, and while I'm talking through it, I'm just going to utilize the new version, so sharedinfrastructure2.yaml. This is the version that's got the changes in, which export the various values that other stacks will consume from shared infrastructure. So let's go ahead and open that, and I'll talk you through the changes that have been made. And the changes are right down at the bottom in the output section of the template. So we'll see the same outputs that we've utilized before. We've got our VPC ID and our 2 NAT gateways, NAT Gateway A and NAT Gateway B. We've got the ID for the public route table, and then for the private route tables, one for AZA and one for AZB. And finally, we've got the application bucket URL, which is used by our application environment template to load the application and test payloads. Now, the only difference between this version and the previous version is we've added export keys within each output block. Now, I detailed how this works in the theory lesson, but what we've essentially done is for any of the outputs that we want available from other stacks, we've added an export key. The export key enhances the capabilities of an existing output, and it enables this output to be referenced from external stacks. So in this case, we've taken a VPC ID output, and we've exported it with the name sharedinf-VPC ID. Now, I've already talked about how this name needs to be unique within this region in your account. And that's because we can reference this name without specifying a stack ID, only within this region. So just to reiterate, this name needs to be unique for any exports within this region within your account. And then we perform the same process with any of the other outputs which the application environment needs to reference. So we've exported the public route table, and we've used the export name sharedinf-public-rt. And then likewise, we've done the same for both private route tables, A and B. And we've used the same naming convention. So sharedinf-private-rta and sharedinf-private-rtb. And then lastly, same process with the application bucket URL. We've exported this one with the name sharedinf-app-bucket URL. And that's the only difference between this and the previous version of the template. We've added exports for any of the values that until now we've had to manually input into the application environment template via parameter entry. So then likewise, let's look at the other end of the equation. Let's go back to our lesson files folder and let's open app-env version 3. And if we scroll down in app-env version 3, you'll notice that we have a lower number of parameters. We're no longer asking for the VPC ID, or the public route table, or the private route table, or the application bucket URL. All of those have been removed from the parameter section of this template. And I'll scroll down and show you how we're referring to those values now. So for example, when we're declaring one of our public subnets that's created as part of our application environment, we're using the VPC ID key, and rather than referencing a parameter, so rather than using this format like we've done in the past, now we're using the import value CloudFormation function, and we're simply referencing the unique export name that's exported as part of our shared infrastructure stack. It's exactly the same syntax and exactly the same result as if we're referencing a local template resource, such as a parameter or another logical resource. The only difference is that rather than referring to an object that's within this template, we're now referring to an object that is within this region, within our account. It's a unique name. So we're referring back to sharedinf-vpcid. And we're following the same process for every other location that references these stack exports. We're using import value and then the unique stack export name. And we're doing the same for the route table association. So rather than referencing that route table ID, we're now importing the value from the stack exports within the account. And the same process for all of the other subnet route table associations. And if you want to carry on looking through the rest of the template, you're welcome to, but the only thing that we've changed in this version of the template is that rather than relying on a large number of parameter values, we're now using the import value to reference those cross-stack exports. So let's implement this and see how it works in practice. So let's go back to our CloudFormation console, and the first thing that we're going to do is to create the new shared infrastructure stack. Now I recommend that if you have an existing shared infrastructure stack, you delete it and recreate it using this version of the template. You don't have to do so. You can just update the stack and supply this new template. But I just want to stress that the majority of the testing that we've done as part of the course development has been done creating a brand new stack. But you're welcome to try upgrading an existing version of the shared infrastructure stack from a previous template version to this one. And if you do have any problems, just open a discussion thread on the Cloud Guru forums and I'll have a look and see if I can help you resolve it. All of the testing that I've done upgrading stacks has worked without problems, but I'd welcome any input from any students who've had other experiences. For this demo lesson, I'm going to assume that you're creating a brand new shared infrastructure stack. And again, I would recommend that you do the same. So click on Create New Stack, upload a template to S3 and choose File. And then I needed to locate the correct lesson files folder. So that's 204 cross stack references. And we're going to implement the shared infrastructure2.yaml file. So click Next and call this shared infrastructure. I'd strongly suggest that you leave the side arrangers for the VPC and the public shared subnet A and B as they are. And I'm going to assume you have done that for this lesson and all of the following ones. Click on Next, Next again, and hit Create. Now this should be familiar by now. You know the process of what resources are going to be created. It's a VPC, it's the subnets, it's the route tables, it's the associations, the internet and the NAT gateways, and all of the other surrounding infrastructure. Feel free to watch this create if you do want to, otherwise you might want to take the opportunity to grab a coffee, a drink or some food. I'm going to pause the video and resume it once this process is completed, and I'd expect the process to take anywhere from 5 to 15 minutes depending on the region and the busyness of the AWS infrastructure. So this process is completed, so we've got a stack in the create complete status. And if you click on outputs, you'll be able to see all of the outputs of this stack, and there'll be an extra column which details the export name of the specific outputs that we've enabled exports on. So you can see shared inf-vpcid, shared inf-public-rt, and so on. So these are the values that we detailed a second ago that are going to be imported into our application environment template or application environment stack. Now, if you have recreated this stack, there is one thing that you need to make sure is the case before you apply the application environment template. We need to go to resources and look for the S3 app bucket. So open this in a new tab. And we just need to make sure that we've got all of the application zip and test.zip files uploaded. So click on upload, add files. And if you open the apps folder in this lesson files and select all of the app files and all of the test files, click on open and start upload. There should be a total of 6 files, app 1, 2 and 3.zip and test 1, 2 and 3.zip. So once that's done, you can return to the CloudFormation console. And we're going to click on create new stack, and this time we're going to apply the application environment template. So click choose file, go back to the 204 cross stack references folder, and this time pick app-env3.yaml. Select that, click next. So I'm going to call the stack app-env test1, and I want you to put 1 for the app version, and straight away you can see that there are a lot less parameters that we need to enter. The only ones that are in any way complicated are the side ranges for the application environment public and private subnets. So we've got app public CIDR A and CIDR B, and app private CIDR A and CIDR B. Now, assuming you've left all of the IP addressing information as default when you created the shared infrastructure stack, which I hope you did, and I'm going to assume you did, then you can continue and enter the same IP addressing information that I'm going to enter here. It will be valid in your account. So 10.20.8.0/24 for the first subnet, 9.0 for the second subnet, 10.0 for the third subnet, and 11.0 for the fourth subnet. So that's 10.20.8.0, 10.20.9.0, 10.20.10.0, and 10.20.11.0, and they're all /24 subnets. So enter those. Make sure you've got dev set for environment and 1 set for the application version, and go ahead and click on next. Click on next again and click on create. So what that's doing, instead of using parameter values, is it's importing all of the other values that we've removed as parameters from the shared infrastructure stack's exports. So straight away, we've improved the ability to apply this template by removing a lot of the manual entry, a lot of the manual parameters. Now, from a flow perspective, the application of the template and the creation of the stack should be identical. It's just that it's getting the values it needs from imports rather than parameters. Now, this might take 5 to 10 minutes to apply, so I'm going to pause the video and resume once this stack has created. And our stack's created successfully. We can refresh and see that all of the resources are completed, and there's no negative problems that we've experienced by using the inter-stack references. We can click on the Output tab and see that we've got our Elastic Load Balancer endpoint, and clicking on this will take us to our application, which should be running on our instance. And there we go, we can see Hello World working version 1, which is the text we'd expect to receive from version 1 of the application. Now, this might seem like a small change, but what we've actually done is reduce significantly the number of parameter values which we need to enter as part of the application of this stack. We've removed the need to supply the VPC ID, the public route table ID, both private route table IDs, and the URL of the application bucket. Now, that's a total of 5 parameters which don't need to be entered as part of the template application and stack creation process. It might not seem like a lot, but the intention is the application of this template is going to be an automated process, and a process which is going to be highly transactional. It's going to be used maybe tens, hundreds of times per day by developers, pre-sales staff, and quality assurance engineers. So the more parameters that don't need to be entered and the less manual effort needed to enter those parameters, the better that it supports our aims of a fully automated deployment process. So this means that we've solved one of these problems. We've solved the second bullet point, the fact that we have to enter a lot of manual information into the template. But what we haven't done is solve the problem where the person applying the application environment template needs to allocate side arrangers for the subnets. We still need to do that, and you saw the fact that I needed to do it during this demo lesson. I told you that you could use the same IP addressing information as I did, but if I asked you to go away and apply 4 or 5 other instances of this application environment template, would you know which IP address ranges to use? You may have networking experience, but you can't guarantee that other people within this fictitious business would do. Pre-sales engineers, quality assurance staff, you cannot expect that they will know how to allocate networking ranges. And even if they did, if these environments are being applied 5, 10, 100 times an hour, you also can't use the same side arrangers that have already been used within other application environments. So this presents us with a problem. We still need to resolve this issue, and we'll do so later in this section. But equally, we've not solved the problem where our automated testing process isn't working when we do stack update operations. And that's something we're also going to look at over the next few lessons. We're going to fix the remaining 2 major issues with the application environment template. And the aim, of course, is that once we've resolved all of these issues, we're free to use this template in a highly automated way as part of the software development and pre-sales processes. Now, before we finish this lesson, you can go ahead and delete the application environment stack. And then once this stack is deleted, you can either leave the shared infrastructure stack in place, or you can delete it. If you do delete it, you may receive an error saying that an S3 bucket can't be deleted while it has contents. If you do get that error, go back to the S3 management console and make sure all of the files in this bucket are deleted. Once you've done that, you can go back to CloudFormation and delete the stack, and that should work. But also feel free to leave the stack in place if you're going to continue this course straight away. I'll assume you're going to delete the stack, and the next lesson will start off with that assumption, and we'll be implementing the shared infrastructure stack again as required. Well, that's the end of this demo lesson, Cloud Gurus, where we've looked at enhancing our templates using cross-stack references. I hope you enjoyed the lesson, and I hope it provided you with some practical experience of how to utilize this fairly new CloudFormation feature. If you have any questions about this lesson or any others, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus, and welcome to this lesson where I'll be talking more about how we can resolve the second of 3 issues with our application environment template. In this case, looking at how we can improve stack updates, or rather, how we're able to test the results of stack updates and rollback if required. Let's jump straight in. If you recall, the initial version of our application environment had 3 major issues. Firstly, the requirement to manually enter many of the values from our shared infrastructure VPC. Secondly, the manual entry requirement of IP ranges and side arrangers for the application subnets. And finally, the fact that while we had tests for stack creation, there wasn't a corresponding test which worked during stack updates. Now, we've resolved the manual information entry for shared infrastructure values by using cross-stack references, and this has approximately halved the number of parameters we need to enter when we create each application environment stack. During this lesson and the upcoming demo follow-up, we'll tackle how we can improve the testing process, extending our automated testing to work with stack updates as well as stack creation. With the current app environment, the creation flow goes like this. We start with an EC2 instance which is created by the application environment template, and of course it's homed inside a subnet also created by the template, within a VPC that's part of the shared infrastructure environment. Now, once the EC2 instance made by the application environment template finishes provisioning, we provide it with some user data via the CloudFormation template. Step 1 of the user data runs a CFN init process against the stack, and it does this to retrieve and execute the CloudFormation metadata associated with this resource, essentially its configuration directives. The first one of these is the configure CFN config key, which installs and configures the CFN HUP process so that the instance can react to any stack updates and update its configuration. The next step is the install www config key, and this installs Apache, PHP, and ensures that Apache is running and set to start up by default. Next is the config app config key, and this is the key responsible for the download and install of the application. It uses the S3 app bucket together with the version number supplied to the stack, and uses this to retrieve the application and the test payloads from the S3 bucket. The test payload is a test file called test.pattern. Its contents consist of a test string which the app should output. Knowing this, it does a HTTP request to the application and compares the actual output with the output expected from test.pattern. The success or failure of this check is reported back to the stack using the CFN signal process. And it's this which interacts with the creation policy on the resource, and the stack creation passes or fails as a result. And that's how the application testing works at a logical level. The problem is that when an update occurs to the stack, even though a new app and test payload are downloaded, the creation policy doesn't rerun. It only operates during stack creation. So the update process has no way to report back to the stack, and the stack has no way to use this as a basis for a successful or failure state for the update. To resolve this, we need to change the architecture of how our application environment infrastructure is provisioned. We need to change it to allow for a resource to be created at every deploy, so that every time we deploy this new resource, we can perform our automated checks and report a success or failure back to the stack. To do this, we're going to use an auto-scaling group, and we're going to do this for two reasons. Firstly, because it meets the aforementioned need. And secondly, because it provides flexibility to allow us to offer a scalable, highly available solution later on. Let's move to the next slide and look at how the new components fit together. We'll start with the same networking structure. So for our shared infrastructure stack, we'll use the VPC which it creates, the VPC-based internet gateway, and the two NAT gateways which will provide the private subnets with internet connectivity. Inside this VPC, we'll create 4 subnets, 2 public ones at the top and 2 private ones at the bottom. Rather than defining the instance directly within the CloudFormation template as with the existing architecture, we're going to define a launch configuration which will store most of the non-runtime configuration elements such as the image ID, CFN init metadata, user data, instance size, the SSH key to use, and the security groups. This launch configuration will be used as a configuration element of an auto-scaling group. But the auto-scaling groups will also define the subnets to use, the minimum number of instances, the maximum number of instances, and the desired number of instances, which will start at 1. But it will also link with our load balancer so that any instances created or destroyed by the auto-scaling group are automatically registered or removed from the load balancer. And the load balancers will also be created by the CloudFormation template for the application environment. So when the template is applied, it makes a launch configuration and an auto-scaling group, which creates the EC2 app server, performs the installation and configuration, and registers it with the load balancers. At this point, the instance, via the config provided by the launch configuration, signals to the CloudFormation stack that it's completed successfully, and that includes the automated tests via the testing definition file. And it references the auto-scaling group. Now the auto-scaling group obviously can have a variable number of instances. In this case it's 1, but it could be many. Now the creation policy count attribute knows how many instances are desired, so it knows the number of instances to expect. In this case it's 1. So the EC2 instance signals to the CFN stack via the auto-scaling group resource, and if the number of EC2 signals match the count attribute in the auto-scaling group's creation policy, it's a success. Now so far the creation flow is similar to the previous architecture where auto-scaling groups were not used. And obviously this time we are using auto-scaling groups and launch configurations. But this is where it gets interesting. On the auto-scaling group, we've specified an update policy. And the update policy controls what happens when a change happens to the auto-scaling group. And we've used the will replace key and set this to true. And this means that if there are any changes to the auto-scaling group, the current one will be replaced. If the update is successful, the first one will be deleted. If not, the new one will be removed and the old one will be maintained. But this means that when we alter a parameter, such as the application version number, the launch configuration is replaced. A launch configuration cannot be updated, so if we change any parameters which are referenced inside the launch configuration, it will force the launch configuration to be replaced. A replaced launch configuration causes a change to the auto-scaling group because the auto-scaling group references the launch configuration. And this means that the auto-scaling group will itself be replaced because of the replace key. Now this means a new auto-scaling group will be created, which will create a new instance, it will deploy a new version of our code, and it will run a new test. If that test works, it will become live, register it to the ALB, Otherwise, the existing version will be maintained. So by using an autoscaling group and the will replace key, we've ensured that any changes to the autoscaling group, or specifically to the EC2 instance definition inside the launch configuration, any changes to that will cause a new set of infrastructure to be created. And that means that our automated test will be rerun every time we have a new application deployment. And that's the end of the theory behind this architectural change of the application environment template. Next, we'll have a demo lesson where we'll look at this in more detail and run through its implementation together. If you do have any questions on this lesson or any other, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus, and welcome to this demo lesson where we're going to look in practice about how we can improve the ability to perform our automated checks of the application by changing the architecture of the application environment template to use auto-scaling groups rather than traditional EC2 instances with creation policies. I think it's worth starting off by demonstrating the problem that we have with the existing template. And to do that, we need to apply the shared infrastructure stack. So make sure you're logged in to the AWS account that you're using for this training. And as always, you'll need access to the lesson files for this demo lesson. The lesson files you'll need are 205 stack update improvements. And you'll get these files either from the course GitHub repository or from the resources section of the A Cloud Guru website for this lesson. Either way, you need the 205 stack updates improvements folder. Now we're going to run through the first couple of steps relatively quickly as we perform them a number of times. The first thing I need you to do is to create a new stack and apply the shared infrastructure version 2 template. So we're going to do that straight away. So locate the folder, 205 stack update improvements, and apply shared infrastructure version 2. We're going to name it shared infrastructure as always. We're going to accept the defaults, click next, next, and create. And I'm going to pause this video and wait till this create is finished, and then I'll resume. And the next thing we'll do after that is upload the application and test bundles into the application bucket. So I'll pause the video and resume once this completes, and it could take anywhere between 5 and 15 minutes. So this has been created, so let's go to the resources tab, and again I'm going to skip through this relatively quickly. We've done this before and it should be familiar. Open the S3 app bucket, locate the S3 app bucket resource, and open it in a new tab. And then we just need to upload the app 1, 2, and 3.zip and the test 1, 2, and 3.zip. And they're used by our application environment to deploy whichever app version you select. And they're within the apps folder in this lesson files folder. So just select all of the files, click on open, start upload, and wait for them to finish. Now I just want to step through the changes that have occurred to the application environment template, because that's probably the biggest and most important thing that's relevant for this lesson. So let's find the lessons file folder, and we need to open app.m4.yaml and app.m3.yaml. And they're the two versions of the application environment, the one that we've altered, which is version 4, and the existing version, which is version 3. Now, as always, when you're completing this lesson, you'll have both JSON and YAML versions, but I'm going to be using the YAML version as the primary version to talk through for this lesson. So if we look at app.m version 3 and we scroll down, and I'm specifically looking for the EC2 logical resource. Now this should be familiar. You know how this works. Basically, there's a creation policy attached to the EC2 instance. It has a timeout of 5 minutes. As part of building the EC2 instance, we perform some user data-based bootstrapping. We install the CFN bootstrap tools, we do a CFN init, and the CFN init runs the CloudFormation metadata. So it uses the desired state directives that are contained within the metadata section to configure CloudFormation, install the Apache web server and ensure it's running, and then download, install, and test our application. Now after that completes, it does a yum system update, curls the local server to test that the application matches the test pattern, and then signals CloudFormation of a success or a failure. So this should be familiar. We've used this version of the template before. Nothing's changed. But the limitation of this template is that this creation policy is only executed or only used during an initial creation of this resource, so during a stack creation operation. If we go back to our CloudFormation console and we create a version of this application environment stack, so let's go ahead and put choose file, go back up to the main folder and pick the application env3.yaml. Click on next and call this app env test1. And we're going to pick application version 1 to install. And for the subnets, 10.20.80/24, we'll always start on that subnet. And then in the other boxes, we'll just copy and paste that in, and we'll change it to 10.20.90, 10.20.10.0, 10.20.11.0. So each time we make a new application environment, we'll just increment all these values by 1. So if I was going to go ahead and create another one, I'd start from 12 and go 12, 13, 14, 15. So let's go ahead and create this. So we're using version 1 and we're using these subnets. So I'll click on next and next again and then create. At the same time, to keep this efficient, I'm going to create another stack, and it's again going to use the application environment version 3 template. So click on open, next, and this time this one's going to be called app env test 2. And on this one, I'm going to directly deploy version 2 of the application, which we know will fail. It's an incorrect application. The output from the application won't match the test.pan, so we know this one will fail directly. But let's do it anyway. So we'll start with 10.20.12.0/24 for the subnet. Again, copy and paste into the boxes, and then change it to 12, 13, 14, and 15. So 10, 20, 12, 13, 14, and 15.0 for each of those subnets, and they're all /24s. We've set it to version 2 for the application and dev for the environment. So let's go ahead and click next, next, and create. So to summarize, application env test 1 is deploying version 1 of the application directly. Application env 2 is deploying version 2 of the application directly. Now what we expect, based on learnings from the previous theory lesson, is that our automated testing procedure only operates during the initial stack creation. So we expect app env test 1 to work because it's deploying a working version of the application. However, app env test 2 we expect to fail because it's deploying a non-working version of our application. What I'm going to do is I'm going to pause this video until both of these stacks have finished. One will fail and one will complete successfully. When we're at that state, I'll resume, and then I'm going to perform an upgrade of app env test 1, and I'm going to change it from version 1 to version 2, just to demonstrate that it will successfully complete when we're doing an update. So even though we're deploying an incorrect version of our application, it won't rerun our automated testing, and it will complete successfully. So if we deploy version 2 directly, it will fail, and if we upgrade a stack from any other version to version 2, it will work successfully, and that will illustrate that our automated testing only works during the initial stack creation. So I'll pause the video and I'll resume once both of these stacks have reached their final state. And we can see that now this is completed, we've got a problem. So as expected, application environment test 1 completed successfully, and application environment test 2, which is the direct deployment of version 2, is in a rollback in progress state. If we scroll down in the events, we can see we received a failure signal from our automated testing. So from CFN signal, we received a failure signal. Now we can demonstrate that our test only runs when we create the stack by updating app env test 1. We'll use the same template and we'll change the application version from 1 to 2. Leave everything else the same, so click next, next, and update. Now this stack will go through an update process, and it should then say update complete or update successful because the automated testing is only running as part of the creation policy during the initial stack creation. And we've identified this as a serious problem with our application template. We need to have a test running every single time a version of an application is deployed, either via a fresh stack creation or an existing stack update. So after a refresh, we can see our app env test 2 is in rollback complete state, and that's the final state that it will stay in. So we know that that's not going to work, so we may as well delete it. So right click and put delete stack. And our app env test 1 has gone into update complete. And that's actually not ideal. We would want it to say rollback in progress because the version that we've updated to is a known faulty version. But it actually says update complete. So not really ideal, but it's exactly what we expected. So we can also now right click on that one and delete it. We're finished with this version of the template. Well, thanks for listening, Cloud Gurus, and this is the end of part 1 of this lesson. If you do have any questions, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to finish this part and continue with part 2. Hello Cloud Gurus, and welcome to part 2 of this lesson. This part continues immediately from where part 1 left off, So let's jump into it and get started straight away. So I want to return to our code editor, this time looking at application env version 4. And I'm going to scroll down to the bit that's changed. So this time, rather than defining an EC2 instance directly, we're creating an auto-scaling group and a launch configuration. The launch configuration contains most of the same information that our EC2 instance had. So it's got the same user data definition, it runs the update of the CloudFormation Bootstrap utilities, it contains a CFN init directive, this time using the launch configuration resource rather than EC2. It runs a yum update, it runs the same curl test, and then it performs the CFN signal operation. And this time, rather than pointing at the EC2 instance directly, which doesn't exist, we're sending the signal to the auto-scaling group. Otherwise, this is exactly the same. We're just defining a launch configuration rather than an EC2 instance. Now with the auto-scaling group, we're obviously referencing the launch configuration. So we're saying that this auto-scaling group references the launch configuration. And we're adding a little bit of extra information here to link this auto-scaling group with our load balancer. And so any instances which are created by this auto-scaling group are automatically registered to our load balancer. We're also defining a minimum and maximum size for this auto-scaling group and a desired capacity. And these reference parameter values. So I've had to add a number of parameter values. We've got desired capacity, which is 1. And then we've got min size, which is 1, and max size, which is 2. So this should, during normal operation, keep the number of instances in this auto-scaling group at 1. Now, the important part of this auto-scaling group is this update policy. What this update policy does is when I make a change to the auto-scaling group, any change which causes an update, it forces a replacement of this group. So it will basically create a new auto-scaling group. It will wait for this to complete or fail. If it completes, it will delete the old auto-scaling group and use this one. And if the new one fails, that will be deleted and will maintain this auto-scaling group. Now you might ask why we do it this way. Why do we go through the effort of creating a brand new auto-scaling group and then removing the old one? We do that because the auto-scaling group has this creation policy associated with it. So every time we make a new auto-scaling group, which is every time we do an update, this creation policy reruns. And this has the effect of making it so that every update we do automatically makes a new creation policy and automatically gets signaled from the EC2 resource that's created by this auto-scaling group. And this is also a change. This count value is traditionally 1, but we're dynamically referencing the desired capacity parameter. Now this might be 1, but you could also update this to 2. This will make sure that it's always expecting the number of signals that equal the number of EC2 resources that get created. So if you have a desired capacity of 1, it will wait for 1 signal. If you have a desired capacity of 10, it will wait for 10. It always aligns with the number of EC2 resources which the auto-scaling group creates. And essentially that's the change. It just means that we have a nice, efficient mechanism for creating a new auto-scaling group with new instances and a new creation policy, both when we create the stack and when we update the stack. So I'm going to go ahead and test this out now. So let's go back to our CloudFormation console. And this time I'm going to create a stack, but I'm going to pick the application environment 4.yaml. You'll see the new parameters, so min size, max size, and desired capacity, and we'll leave them at defaults, 1 for min, 2 for max, 1 for desired. And for the application version, I'm going to start off with version 1. For the stack name, I'm going to put app-env asg test1 for application environment auto-scaling group test1. And then in the subnet parameters, we're going to use the same subnet side arrangers that we've used before. So 10.20.8.0/24 for the first one. Cut and paste these in each of the boxes and just increment 1 each time. So 10.29, 10.20.10, and 10.20.11. Leave everything else as it is and click on Next. Next again, and click Create. And what this will do, and we can look at the event log in detail for this one, so we'll keep refreshing, is this will start by performing the same subnet creation that the previous version of the template did. So no change so far. Once those subnets have created, it will go ahead and create the launch configuration and then the auto-scaling group, and that's where the process changes. So we can see it's created the launch configuration, it's doing the other details, so the subnet route associations, It's creating our elastic load balancer. And once this progresses, we'll see that it will create our auto-scaling group. If we go to the Resources tab, we'll get a little bit of a cleaner view. So it's created the launch configuration and the load balancer, and now it's creating the auto-scaling group. And as part of this process, because we have a desired capacity of 1, it will go ahead and create a single EC2 instance. And we can verify that if we go to Services, and then we open the EC2 console, running instances, and we can see that we're initializing one T2.micro instance in this region. So the end result is the same. We still have an EC2 instance that gets created. It's still running our user data. It's still bootstrapping itself against the CFN metadata, and it's still signaling its success status to CloudFormation, only now it's signaling the auto-scaling group rather than an EC2 logical resource. So let's go back to CloudFormation and do a refresh. And we can see that it's still creating progress. Now this might take a couple of minutes to move to its final state. It might take anywhere between 5 and 10 minutes. So I'm going to pause the video and I'll resume it once we get a status change. So this has changed to create complete, and it didn't actually take that long. It was only 2 to 3 minutes. If we click on the Events tab, we can see that it received a success signal from this instance. So the process, the flow of our automated testing is pretty much the same. We changed the way that we create the EC2 instance and where the signal occurs, but the process of bootstrapping and signaling is architecturally the same. Now I want you to click on Resources and pay attention to the auto-scaling group physical ID. So it ends in WGYU, Whiskey, Golf, Yankee, Uniform. So keep that in mind. What I'm going to do is right-click on this stack and put Update. I'm going to leave the template as the same template. This time, I'm going to change the application version from 1 to 2. 2, of course, being the version of our application that intentionally doesn't work. So click on Next, Next again, and we'll wait for CloudFormation to compute the changes that are going to happen. And by changing the application version, we modify our launch configuration logical resource. We know that CloudFormation can't modify a launch configuration. A launch configuration can't be modified anyway, even if you're doing it from the console. So that gets replaced. A change to a launch configuration also changes our auto-scaling group. And that change is listed as conditional. And it's conditional because it can cause replacement, or it can be done in place, depending on the value of this auto-scaling replacing update key. And of course, we've got it set to will replace. So let's go ahead and click on Update, and we'll monitor the process. So there's an update in progress status for the CloudFormation stack. The security group requires a new physical resource. So that's being replaced. It's initiated the resource creation of that security group. We're making a modification to a launch configuration, and that also requires the creation of a new physical resource. Here is where it's creating a new auto-scaling group, and it's doing that because we've requested one. And we've requested it by setting this key, the will replace true. And what we'll notice if we go to the EC2 management console and we refresh, we'll see that we're getting another instance while the existing instance is running. And that's critical. The reason for that is that CloudFormation is going to create a brand new auto-scaling group. If we get a successful status to that auto-scaling group, to the new one, it'll go ahead and remove the old auto-scaling group, which will remove the old EC2 instance. But if we get a failure, which will be the case in this example, then what will happen is the new auto-scaling group will be deleted and the existing one will continue to function as part of this stack. So I'm going to pause the video here and wait until we get a status change. You should continue watching this if you're doing it within your own environment, and I would expect to see a failure signal received from our EC2 instance, and that should cause a rollback. It should cause the deletion of this new auto-scaling group, and the existing auto-scaling group will be maintained. So we won't see any change in the physical ID of the auto-scaling group in this specific example, because we're actually changing it to a bad version of our application. And we can already see that's happened. So we've got an update, rollback in progress. Check out the event log. Receive 1 failure signal out of 1, unable to satisfy 100% min successful instance requirements. And so it's going to go ahead and delete this new auto-scaling group. Let's wait for the rollback to complete. It'll perform a cleanup. You can see it's deleting the new auto-scaling group. This is the new physical ID, not the existing one. I'm just going to keep refreshing this. I think it's important to step through the events that happen in real time. If we go to the EC2 management console As expected, our new instance, the one that was created as part of the new auto-scaling group, is being shut down and eventually it will be terminated. And this is happening because we got the failure signal to the auto-scaling group. If we go on the resources tab, we can see that the physical ID of the auto-scaling group has been returned to the old physical ID. So the Whiskey Golf Yankee uniform. Now this might take a couple of minutes, so I'm going to pause the video and I'll resume it once this rollback process has completed. So the rollback completed, and we can see the stack's now in an update rollback complete state. So now, update the stack again, same template, but this time we're going to change the application version to 3. And this is a version of our application which we know to be successful. The test.pattern output will be the same as what the application generates. So click on next, next again, and then update. Now this will go through the same process. So it will attempt to create a new auto-scaling group with a new instance which will provide a new signal to that auto-scaling group, either success or failure, and we're expecting it to be a success. But this time do pay special attention to the auto-scaling group physical resource ID. So Whiskey Golf Yankee uniform. What I'm expecting at this point is that this will create a new auto-scaling group with a new physical ID. The signal from our new EC2 instance will be a success, and that will cause the old auto-scaling group to be deleted. So keep an eye on the event log. I'm going to pause the video until this process completes, and then we can just review the changes that have occurred to the stack. So this is almost finished. The stack is in update complete, cleanup in progress. And what this is doing is we've received a successful signal from our new instance as part of our new auto-scaling group. And we can see that because our auto-scaling group physical ID has changed to the new one. So what's happening now is we're deleting the old auto-scaling group. If we go to our EC2 console and do a refresh, we can see we've got our new instance and our old one has been terminated. So any second, the stack should change into an update complete status. It's just deleting the other resources, so the old launch configuration, which should be relatively quick. And at that point, as we can see, the stack changes to update complete. And that's pretty much the end of this lesson. We've demonstrated how by slightly changing the architecture of our template, moving from a static EC2 instance to an auto-scaling group, we've enhanced the capabilities of our automated testing process. We've made it so that each time we do an update, we get a new auto-scaling group. And that auto-scaling group comes with a new creation policy. So whether we're doing a stack create or a stack update, we're getting the same automated, rich testing occurring on each instance. And that means we've resolved the second of our 3 major template problems. And that's the bottom one. We've now got a test for success or failure on stack updates. And that's a big deal. We've resolved 2 out of 3 of these problems. In the upcoming lessons, we'll look at how we can resolve the entry and allocation of IP side arrangers for our subnets, so the public and private subnets. But right now we've done well. We've fixed 2 out of 3 of the serious problems with the template. So that's the end of this lesson, Cloud Gurus. I hope you've enjoyed it, and feel free to delete both the application env ASG test 1 stack. Now once this is completed, please do delete the shared infrastructure stack. The next demo lesson is going to do some pretty extensive modifications to both our application environment stack and the shared infrastructure stack, and it's going to introduce a new stack to provide the automated selection of IP addressing. So it's just going to be much easier if you delete the shared infrastructure stack. It'll just make sure that we have no problems when it comes to the next demo lesson when we're implementing our custom resource. So wait for this to finish, and then go ahead and delete the shared infrastructure stack, and then this lesson's over. If you do have any problems deleting the shared infrastructure stack, then go ahead and go to the S3 management console and manually empty any buckets you have which are called shared infrastructure S3 app bucket. Once you've manually emptied those buckets, you can go back and delete the shared infrastructure stack and it should work fine. It might just complain about doing so if those buckets have any files in them. So go ahead, delete both of those stacks and then complete the lesson. If you do have any questions about this lesson or any of the others, then please do reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus, and welcome to this lesson where we'll be discussing the basics of Lambda and how it can be used to interact with AWS services. We're going to start with a Lambda introduction for those students who haven't used the product before, and then in the next lesson we'll look at how it interacts with CloudFormation specifically. So Lambda is a function as a service or FaaS product. This means that you provide AWS a function, i.e. a piece of code, and AWS execute it. Unlike traditional compute, you are only billed for the number of milliseconds that your code runs. You don't pay for any idle time. Lambda functions run in an isolated environment. They can't see or be influenced by other running functions. Additionally, they're stateless. They start in the same clean state every time they execute. Now you're responsible for the persistence. The environment that Lambda runs in, by default, has no access to information about previous runs or any existing states. All it gets is an incoming payload, and more on this in a second. And it doesn't, by default, maintain any result after it terminates. You're responsible for storing any result payload in another service. It's critical that you understand there's no data maintained inbound and no data maintained outbound. You run something, you act upon some data that you retrieve or you pass in, you generate a result, and you put the result somewhere. So let's have a look at how Lambda functions are invoked. First, Lambda is an event-driven product. So it starts with an event. And we'll look at what these events are in more detail in a second, but just assume that AWS tells a Lambda to start based on something happening. Along with the instruction to start, AWS generates some event data. And this data and the format of the data is dependent upon the type of event and the circumstances of the event, so how, when, and where. But this event data is passed into the Lambda function as it runs. The function accesses this data, performs some compute operations, and optionally generates a result. It's important to understand that a Lambda might not generate anything. It might simply interact with incoming data, or interact with other AWS products as a result of the compute activity, or it may make internet HTTPS calls, or optionally it can generate something. If it does generate something, Lambda can write that result to a destination, or it can generate its own event, which may include interacting with an internet web service over HTTPS, or another AWS service over SNS or SQS. Or it could invoke another Lambda function. The possibilities are many, but it's an executing function, so it can do pretty much anything that an application can do, with some limits. It's obviously critical to understand that at no point do you as a user or operator of this service have access or visibility to any servers. Your unit of compute or your unit of abstraction in this case is a function. You run your function, you build for the run of that function, you send your function some data, it optionally generates some data, and you store that data. You have no exposure to the server operating system or server infrastructure. Now in terms of the type of events that can be used to spawn Lambda, there are many. AWS have done a fantastic job at their product integration, but let's spend some time looking at a few ones quickly. So we'll start with Lambda. Now a fairly common design pattern when using Lambda is together with S3. A Lambda function can be configured with a trigger which invokes the function when a file arrives on an S3 bucket. So every time a new object is added, every time an object is deleted, or every time an object is updated, a Lambda function is invoked, and it's passed as the incoming piece of metadata the details on which object has been updated, deleted, or created. This means that you can act on new objects in an event-driven, real-time way. For example, adding watermarks to images, generating thumbnails, or performing simple workflow-style operations. Now a similar architecture could be used with simple email service, or SES. Each time a new email arrives, a Lambda function could be invoked and perform some actions. This might be stripping file attachments or performing an automated response. And note, SES can be outgoing also, so the Lambda function could provide an email response at the conclusion of its processing. Now the same is true for DynamoDB, which can be configured to invoke a Lambda function each time data is changed within a table, and this can be used to implement DB trigger-style functionality, which allows for real-time event-driven data processing or summarization, a very powerful feature. And finally we have CloudFormation, and this can interact with Lambda in a bi-directional way to extend its functionality. And we'll talk more about this in the next lesson. For now, just know it's possible. So now we need to know about some of the capabilities of Lambda. Let's look at the data that it receives during an invocation. When a Lambda function is invoked by an event, it receives two main inputs, the context object and an event object. The context object contains methods and attributes, and it's used to allow the function to obtain certain information about its invocation. For example, we can use it to get the remaining time in milliseconds that the function has to execute. There are limits, as we'll see on the next slide, and the context object is often used to provide access to these limits. Now we can also query attributes of the context object to identify the function name and the version of the function, or to assess the memory limit in megabytes, or the log group and stream name used for the function. Context is important. It allows the function to see metadata relating to its invocation or its runtime environment. The event object differs based on what the event is. In some cases, there is a single data structure. For example, when Lambda is invoked by a scheduled event, i.e. a cron, in that case there is only one structure within the event, and it might look something like this. It's JSON, and you can obtain information about the event from the object attributes. In other cases, event may contain many records. It could have 100, for example. If you're using Lambda with DynamoDB and it's a table with a high number of transactions, then a single function could be invoked with multiple of those transactions. You need to know the structure and how to process it, and I'll make sure there's a link on your screen now which shows the event structure for many common event types. In the next lesson, we'll use Lambda with CloudFormation, so we will need to know the correct structure to use, so please do review the link that's on screen now. For now, just knowing the high-level architecture is enough. Now, there are limits with Lambda, and in this case, I'm talking technical limits, not feature ones. Let's quickly step through a number of them which may impact you at some stage. A really important limit to know is that the local temporary disk space within your function's runtime environment is 512 megabytes, and that means that you're limited in the amount of local disk space that you can utilize. If you need more, you'll need to utilize services such as S3 to store larger files. Also, you have a limit of 1024 threads and processors combined. Keep that in mind for larger multi-threaded applications. And finally, there's also a hard limit on the execution time of a Lambda function. And this is 300 seconds or 5 minutes at the time of creating this lesson. You can't currently get any longer. It's a hard limit for a single invocation. Now, you can perform processing and then spawn another invocation to continue running, but this comes with its own set of technical challenges which you need to overcome. Well, that's the end of this lesson, introducing Lambda. In the next lesson, we'll look at how we can use Lambda directly with CloudFormation, specifically using CloudFormation custom resources backed by Lambda. If you do have any questions on this lesson or any of the others, please reach out directly via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus, and in this lesson we're going to look at CloudFormation custom resources, specifically using Lambda to provide the custom resource functionality. Now, a good first step is to look at what a custom resource does and how it can be used to extend CloudFormation. So let's jump right into it. Before we speak about custom resources, it's worth looking at an architectural level how traditional CloudFormation resources operate. Let's consider a simple example, an EC2 instance, which is a simple, standard, traditional and supported CloudFormation resource. We start with a CloudFormation template. The template defines a number of resources, one of which is our EC2 instance, and this resource is a logical resource. It's identified by a logical resource name. For example, we've used EC2 in many of the lessons during this course to refer to an EC2 instance. Now, CloudFormation as a platform sits in the middle, and it manages these resources as stacks. And as we've learned, stacks represent the state and configuration of objects. It offers grouping together with configuration and lifecycle management of resources. CloudFormation parses and evaluates templates. It looks through a template evaluating the configuration of each of the logical resources defined in the template. So it's looking at the resources template definition time information. And it also looks at parameters entered at the time of stack creation. At a basic level, it uses the template, so the logical resources, together with any parameters, and it creates one or more physical resources. And it does this by orchestrating the resource creation, update, and deletion with the various AWS services, or rather, the AWS service endpoints. Now, by now, you should understand that logical CloudFormation resources have properties. And the properties are the resource inputs or configuration options. And we also have resource attributes, which are the outputs of the resources. Now, the same is true of physical resources, whether created via CloudFormation or done manually. Just think about when you create an EC2 instance, how you have to specify an Amazon machine image, a subnet, and an instance type. And how you can also read those values and other values afterwards using the CLI API or console. It's the same concept, properties and attributes, inputs and outputs. Now, the job of CloudFormation when we use it in its default way is to manage the relationship between logical resources and physical resources. And it does so via the stack object. If you change a logical resource, you'll change a physical resource. It either gets updated or replaced. And it also follows that when you remove a logical resource, the physical resource also gets removed unless you have a specific deletion policy set on that resource. When you delete a stack, you're essentially removing all of the logical resources which that stack manages, thereby deleting the physical resources, and this again assumes no specific deletion policies. So that's standard resources, and you use standard resources when you're interacting with supported AWS resources such as EC2, RDS, and many others, or when you're utilizing a feature that's fully supported by CloudFormation and you're using a feature of those resources that's fully supported by CloudFormation. For example, you can create an S3 bucket with CloudFormation, but you can't create files in that bucket. Now, when either of those aren't true, for example, when you need to interact with an unsupported service, or you need to utilize a feature of a supported service which is not supported by CloudFormation, then that's when you need to use custom resources. So what are custom resources? Let's have a quick look at the architecture of those on the next slide. A custom resource starts in much the same way as a standard resource. They're still defined in CloudFormation templates. They're sometimes alone, or sometimes they have other traditional or custom resources alongside them. Now, custom resources still have properties or inputs, but they also have something called a service token. And we'll talk about what a service token is in a moment, but essentially it's an endpoint address. Now, custom resources are still managed by CloudFormation, and this still happens via the stack construct. But this is where the flow diverges from that of a standard resource. CloudFormation can't talk to an AWS endpoint to create this resource, and it can't do so because you might be trying to interact with an unsupported AWS product, or you might be trying to interact with a system outside of AWS. And this is a critical learning objective. Custom resources allow you to extend CloudFormation to non-supported or external to AWS systems. Custom resources interact with resource providers, and they do so via SNS, which is Amazon's simple notification service, or they use AWS Lambda, which is AWS's function as a service product. In both cases, these services have an endpoint, and it's these Lambda or SNS endpoints that your service token property on your custom resource points at. So the service token property that you define on every custom resource, and it's specific to that custom resource, points at a simple notification service or AWS Lambda endpoint. Now, you know by now that a stack can undergo one of three main operations, or three main states: create, update, and delete. When a stack with a custom resource goes into one of these states, each custom resource sends an event or a message to its service token endpoint, and this is known as a request. That request event or message is either create, update, or delete. Along with the operation type, which is known as the request type, there are a few other pieces of information which go along with these requests, and we'll detail those on the next slide. But for now, the most important one to know about is that there's a response URL contained in the request. And the response URL informs the resource provider how it can deliver a response back to CloudFormation. The request event is received by Lambda or an external application notified via an SNS topic. Some processing occurs, and this processing generates a response payload, and this response payload is sent back to CloudFormation via the response URL endpoint described above. The response, as well as containing some data, which we'll talk about shortly, also contains a status, i.e. success or failure. That response, so the status and any data, is made available to the custom resource, and it can be accessed via any of the resource's attributes. Now, it might be hard for you right now to visualize how this is useful. I remember when I first learned about custom resources, I actually didn't see the point, because at that point there were very few real-world examples. Consider though for a moment that the Lambda function which is executed when a request event is generated by a custom resource can do anything that it wants to. It could create an instance of a non-supported resource, it could do some custom compute on pretty much any data, it could just list the files in an S3 bucket and pick the latest version, or it could run some aggressive testing against an application being deployed by your CloudFormation stack. The possibilities are endless. The architecture is always created the same. The custom resource is defined in the template, and it has some properties and a service token. It's created, updated, or deleted depending on the state of the resource. The resource provider receives the request payload via its endpoint, i.e. SNS or Lambda. It does something and it returns a success or failure along with optionally some data. The stack reacts to the success or failure as it would a normal resource. If it fails, the create, update or delete will also fail. If it succeeds, processing will continue and any data in the response payload can be accessed via the get attribute function, just as with a normal resource. You can orchestrate pretty much anything you can code with custom resources, and they offer a way to integrate with any product or system capable of receiving SNS notifications and posting HTTP responses to a CloudFormation endpoint. Pretty much any system can be extended to do so, and if it can't, middleware can help provide this extension. Let's have a look at the request and response exchange on the next slide. An outgoing request payload has the following syntax. It has the request type, which is create, update or delete, and it's important to note that this is not a property defined on the custom resource. This value is provided by the stack as part of a create, update or delete operation. The request ID is a unique ID generated by CloudFormation for this specific request, and it can be used by the resource provider to track and log individual requests. The response URL we've already covered, and it's the way for the custom resource, i.e. the Lambda function, to respond to this request. Resource type matches the type specified by the resource, and in CloudFormation, this can be AWS CloudFormation custom resource or custom anything. The function or the resource provider can use this to determine what type of custom resource generated this request. Next, we have the logical resource ID, and this is the template logical resource name for the resource. Again, this can be used by the function to react according to the logical resource name. Next, we have physical resource ID, and physical resource ID is an optional attribute and is only used for stack update and stack delete operations. You receive a physical resource ID from a custom resource when it's first created, and you can then supply it back during update and delete operations, and this allows the resource provider to coordinate the update or deletion of physical resources in the background. Next, we have stack ID. And the stack ID is the ID of the stack, and this again is provided by CloudFormation. It's not contained within the logical resource definition. And finally, we have the resource properties, and resource properties is an object or dictionary data type which contains all of the properties given to the custom resource within your template. So any properties that you pass to a custom resource will be contained within this structure. And the structure on screen is an example of the data that a Lambda function would receive when it's used to back a custom resource. The event structure that a Lambda function gets when it's invoked by a CloudFormation custom resource would be this structure. So the stack ID attribute of the event object would be the generating stack ID. And don't worry if this looks complex, I'll go through it extensively during the demo lesson. Now, the exact format can differ between a create, update and delete request type. For example, with an update, there's another object, old resource properties, and this contains the properties of the custom resource before the change, so before the update. The response format differs depending on a few things. It depends if the processing was a success or failure, and it depends on the type of the request. For example, for a create event, this is an example response payload for a successful process. You should always return a success status, and you can copy a lot of the fields from the original request, like the logical resource ID, the request ID, and the stack ID. You should also provide a physical resource ID and optionally a data structure in the data key. This is the part that will be accessible using the get attribute function on the CloudFormation side. So just imagine that the custom resource has been created, CloudFormation sent you a piece of data saying please go ahead and create this resource. You want to give CloudFormation back a status, so success, and you also want to give it back a physical resource ID because remember CloudFormation is managing the link between logical and physical resource IDs. So for this logical resource creation, you want to give it back a physical resource ID. And you also optionally want to give it back some data, and the data is the thing that can be accessed by using the get attribute function on the logical ID of the custom resource in the CloudFormation template. If your Lambda function or external system decides to return a failure, you need to provide the status of failed, and you need to provide a reason. The failure reason is mandatory if it fails, and it's optional if it succeeds. Additionally, as with a success, you can copy the logical resource ID, the request ID, and the stack ID from the original request. So if something fails, the only difference really is you need to provide a reason for the failure. And that can be something as simple as request failed or function failed, but there needs to be a reason. Now with both, and this is critical, this response is sent back to CloudFormation using the response URL. And the response URL is something that was contained in the original request data, which is processed by your Lambda function or your external system. So a lot of the information that you feed back to CloudFormation can be copied verbatim from the original request data. So keep that in mind, and we'll look at this during the demo lesson. So that is how custom resources work from an architectural and data exchange perspective. It's an extremely powerful feature, and one that combined with Lambda and/or SNS allows you to extend almost indefinitely the capabilities of CloudFormation. Anything that can be achieved using the AWS APIs can be done using Lambda and custom resources. Any external service which can be interacted with via HTTP, HTTPS, or API-based endpoints can be utilized by Lambda plus custom resources. So keep that in mind. It's an extremely powerful way of extending CloudFormation's capabilities. Now spend some time before moving on to the next lesson thinking about how the application environment template can be extended using custom resources and Lambda. And specifically focus on ways that this can be used to improve automation. And we'll see if we've had the same idea when we look at the next lesson. Well, thanks for listening, Cloud Gurus, and that's the end of this lesson. I hope it's been really useful. If you do have any questions on this lesson or any others, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus, and welcome to this lesson where we'll be discussing the theory and the architecture around extending the functionality of CloudFormation using custom resources. Specifically in this case, we'll be developing an auto selection of subnet side arrangers using a custom resource. I identified at the start of this section that the application environment template had three major issues. The first issue is that information had to be manually entered at every application of the app environment template, and we solved that together by using inter-stack references. We've also seen how the template wasn't capable of running a test for a successful application deployment when doing stack updates, and we fixed that together by changing the deployment method to use auto-scaling groups and setting the template to replace the auto-scaling group each time the template was updated. And this, together with the creation policy, allows us to run a successful application test, either during a create stack or an update stack situation. And the last problem is that the current application environment template still requires manual input to decide on the subnet side arrangers to use each time the template is applied. And this means it needs networking skills that not everyone has. And this limits our ability to use the template in a highly transactional and highly automated way across the business. It's this problem that I want to work through solving with you next. In this lesson we'll look at the theory, and in the demo lesson we'll implement it together. So let's just refresh ourselves. Let's understand what the problem is. The visual aid on your screen now is the Shared Infrastructure VPC. It provides a VPC, internet gateways, route tables, NAT gateways, and two public subnets for the NAT gateways to operate in. It has an IP or side range for the whole VPC, and the two public subnets within the VPC use IP address ranges within this VPC side range. What remains within this VPC side range is available for our application environments. The current method is that each time we apply the template, and by we, it could be you, another human, or ideally a software process, but the ability to use a software process is heavily impacted by the fact that we have to enter this subnet IP address range information manually. Every time the application environment template is applied, it creates four subnets. Two private subnets, one in each availability zone, and two public subnets, also one in each availability zone. And we need the ability to apply the template multiple times, and when we delete one of the application environment stacks, we need to release those subnets and allow their reuse when we apply another instance of the template. And we can't be in a position where one application environment template uses the same IP ranges as another, as this will cause a clash. And the chances of these clashes occurring become much more likely if it's a highly transactional environment and if humans are controlling the process. The problem is that CloudFormation offers us no way to auto-generate the subnet IP ranges. The logic behind doing so is pretty complex, and it's well beyond the capabilities of CloudFormation. Luckily, we have custom resources, and we'll be using this feature to extend CloudFormation's capabilities ourselves during this theory and the next demo lesson. So let's move on to the next slide and look at the architecture. Our architecture begins with our shared services VPC, and by default it has a CIDR block of 10.20.00/16. Within this, by default, are two subnets, which have the CIDR blocks of 10.20.00 and 10.20.40/22. These subnets are always present, and the IP addresses that they use always exist within our VPC. We can think of them as reserved. They're not available for use by the application environment. And this leaves the rest of the VPC free for our application environments. So any IP range from 10.20.80 to 10.20.255.255 is available for our application environments. We're going to adapt the application environment template so that it has a custom resource in addition to the 4 subnet resources. The custom resource is going to be configured to invoke a Lambda function, and that Lambda function will be created by another stack and template we'll use called AutoSubnet. And the AutoSubnet template will also create a DynamoDB table called AutoSubnetTable, and more on why in a second. Now, our custom resource will use inter-stack references heavily, and it will do so to pull some shared values from the shared infrastructure stack, such as the VPC CIDR block and the reserved subnets, and it will also pull information from the AutoSubnet stack, such as the table name, which will be used to allocate these IP address ranges. So this information, together with the stack ID of the application environment stack, will all be put together in a create request. And this create request will go to our AutoSubnet Lambda. At this point, Lambda will use the VPC CIDR block information provided by the custom resource, and it'll search through all of the available Class C subnet ranges within the VPC, and Class C, as we know, are /24 address ranges. For each one of the IP address ranges identified, it will perform 2 checks. The first check will look at whether the range identified is used already by the infrastructure VPC public subnets, so the 10.20.00 and the 10.20.40. And if it is, it will be discarded. If not, the Lambda will then look at if it's already allocated, and it will do this by checking the DynamoDB table. It will continue and attempt to find 4 IP address ranges, so 4 CIDR ranges, 1 for each of the subnets. Once found, it will store each of these in the database along with the stack ID of the application environment which they're allocated to. And assuming this process is successful, it will deliver a success response to CloudFormation, and the 4 subnet CIDR blocks will be available for reference by the subnets in our application environment template using the get attribute function. Now, when we delete our stack, CloudFormation will attempt to delete the custom resource. When it does so, a delete request will be passed to the AutoSubnet Lambda function, and the Lambda function will then search through the DynamoDB table and will unallocate the subnets used by this stack, and that will free them up to be available for other instances of the application environment stack. Essentially, because it's recorded within a DynamoDB table, no 2 application environment instances can use the same set of subnets. We can't have any clashes. When an application environment stack is created, subnets are allocated, and when it's deleted, the subnet allocations are removed and can be reused over and over again. This process should be highly efficient and should be capable of coping with highly transactional environment creates and deletes. Okay, and that, at a high level, is the theory and architecture behind our CloudFormation capability extension. When implemented, it will remove our last remaining problem with the application environment template, and it will allow it to run in a fully scalable and automated way. In the next lesson, a demo will implement this architecture together, and we'll run through how it works from a practical perspective and how it improves our template and allows us to support a fully automated and scalable application deployment mechanism. Okay, thanks for listening, Cloud Gurus, and that's the end of this lesson where I've detailed the theory and architecture behind how we can extend CloudFormation using custom resources. When this is implemented, it will remove our last remaining problem with the application environment template, and it will allow us to run it in a fully scalable and automated way, something that we'll demo in the upcoming demo lesson. If you do have any questions on this lesson or any others, then please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next, which will be the accompanying demo lesson. Hello Cloud Gurus, and welcome to this demo lesson where we're going to look at extending the capabilities of CloudFormation using Lambda-backed custom resources. As explained in the theory lesson, we're going to specifically look at how we can use a Lambda-backed custom resource to provide automatic selection of the side arrangers for the subnets within the application environment stack. So let's get started straight away, and as before, I'm going to skip through fairly quickly some of the steps that we've done before multiple times and only stress the changes that have occurred. The first thing is I want you to be logged in to the AWS account that you're using for training, and you'll need access to the lesson files, and these are in a 206 Lambda Custom Enhancements folder. And you can obtain this either from the resources section of the Cloud Guru website or as part of the course files that you've downloaded from the GitHub repository for the course. Now, as always, we've got two different versions of the shared infrastructure and two different versions of the application environment. The lower number is the existing old version, and the higher number is the one which has been enhanced for this lesson. Now, in addition, we also have a third template, an auto subnet template, and we'll talk about this more in a second. This is the template that adds the functionality required for the automatic subnet selection. Now, when you're performing this demo, you'll also see JSON versions of all of these templates. Don't be surprised, we're using YAML as the primary version for this demo, but by the time you're performing this demo, there'll be extra files in this folder that are the JSON versions. First thing you need to do is to go to the CloudFormation template and upload the new version of our shared infrastructure stack. So locate the lessons file folder, so it's the 206 folder, and select the shared infrastructure version 3.yaml. Now, as always, call this shared infrastructure. Leave all the other values as their defaults, click next, next, and create. Now, this will take some time to create, and while this is doing so, move to the lessons file folder, and I want to show you the changes in the shared infrastructure version 3. So I'll go ahead and open that, and we're doing a number of new things. The first thing we're doing is we're creating a Lambda bucket, and this Lambda bucket is a bucket that will store the source code within a zip file for our Lambda function that will automatically select the subnets to use. And this is the definition for the logical resource S3 Lambda bucket. Don't worry about it for now, it's exactly the same as the S3 app bucket. It's just called S3 Lambda bucket. Everything else is the same, we're using the same bucket policy, so it's full free access to anyone on the internet. And again, you might decide to tighten the security if you're using this in production, but this is just a proof of concept. The other change, if we scroll down to the bottom, is the addition of a new output called Lambda bucket, and we're also exporting this as a stack export, so it's called shared inf-lambda bucket. And this will be used by the auto subnet stack to load and create the Lambda function. So this is the bucket that the Lambda function zip file will be uploaded to in a second, and the auto subnet stack will obtain the details for this bucket by looking at the stack export. So that's the only difference. It's basically the addition of one new bucket and the addition of one stack export. So this might take a couple of minutes to create the shared infrastructure stack. So while it does, I'm going to pause the video and I'll resume it once this is completed. So this is completed, and we just need to do a number of things to tidy up and finish the setup of the shared infrastructure stack. So click on resources and scroll down to the bottom. Specifically, we're after the S3 app bucket and the S3 Lambda bucket. So right click on both of these and open them in a new tab. Now with the application bucket, I need you to add each of the application and test zips into this bucket. So app 1, 2, and 3, and test 1, 2, and 3. So upload all of those into the application bucket, the S3 app bucket. Once that's completed, you can close that tab. Next, in the Lambda bucket, so S3 Lambda bucket, you need to upload from the lessons file folder the auto-subnet.zip file. And this is a zip file that contains our Lambda function. So select that and click on Start Upload. And once that's finished, you can go ahead and close this tab. We won't need it anymore. So next, we're going to create the auto subnet stack. And while this creates, I'm going to step you through how it functions. So click on Create Stack and choose from the Lesson Files folder the auto-subnet.yaml file. Click on Next and simply call this stack auto-subnet. There's no further parameters that are needed. Just go ahead and click on Next. Next again. Accept the fact this might create some IAM resources. Specifically, it's making a role that Lambda will use to access DynamoDB, and I'll talk more about that shortly. So tick the box and click on Create. Now, while this is creating, I want to step you through these new moving parts. So go to the Lessons File folder. Let's first look at the auto-subnet.yaml file. And this does a number of things. The first thing is it creates a DynamoDB table. And that DynamoDB table has two values, a CIDR range and a stack ID. And that's all it does. The CIDR range is the hash key of the table, and the stack ID is an attribute. We also create an index, so we can look up either based on the CIDR range or the stack ID. We can say for a particular CIDR range, which stack ID does this belong to, and for a particular stack ID, which CIDR ranges are allocated. And I'll talk more about that in a second. We also create an IAM role that can be assumed by Lambda, and the policy associated to that role allows that Lambda function to log to AWS CloudWatch logs and also to perform any DynamoDB operations on either the table that we just created or any indexes of that table. And finally, we create an actual Lambda function, and the Lambda function is referenced by importing the name of our shared infrastructure Lambda bucket, which we just created as part of the shared infrastructure stack, and it assumes that the zip file is called auto-subnet.zip, and that's the file that we just uploaded to that bucket a moment ago. So this template essentially creates our Lambda function together with the roles that the Lambda function needs to operate and the database table that the Lambda function needs to store the IP allocations. And then as outputs, we output the Lambda function ARN. And of course, as well as being outputs, we export both of those details. So we export the Lambda function ARN and the database table name as stack exports, which are available to any other stacks that are running in this region in this account. So that's the auto subnet stack. Now also, if you expand the auto subnet folder, if you do want to look at the source code of the Lambda function, just open this auto-subnet.py file. Now, I'm not going to spend a lot of time detailing what this function does because I can't assume all of my students are software developers. Essentially what happens is this Lambda function is provided a table name, a stack ID, and a region, and those details are provided via CloudFormation. We're also provided with a VPC CIDR range and a request type. The VPC CIDR range is provided by the custom resource and the request type by CloudFormation, whether it's a create or an update operation. Essentially, we get all of these variables which are needed by this function to process and to allocate IP addresses. Some of them are provided by CloudFormation directly, some of them are given via properties on the custom resource. So essentially what we do at a high level is we determine whether the operation is a create operation or a delete operation. If it's a create operation, then we basically look at the VPC CIDR range and we split it into class C subnets, so /24 subnets. And we iterate through all of those subnets to check whether they match the reserved subnets for the shared infrastructure public subnets. And if we do, we discard them. What remains are subnet addresses that can potentially be used for our application environment subnets. And we then look at the DynamoDB table to see whether those subnets have already been allocated. And if they haven't, they can be allocated for this stack. So we basically get 4 CIDR ranges, 4 IP address ranges that can be used for this instance of the application environment that we're going to be creating in a second. And then we store them in the database. We store the CIDR range and we store the stack ID to which those CIDR ranges are allocated. And then we return those values to CloudFormation and we call them app public CIDR A, app public CIDR B, app private CIDR A, and app private CIDR B. And they're available to be referenced in our application environment template using the get attribute function. Now, if it's a delete operation, we perform the inverse. We do a search on the table looking for any items which match the stack ID which we're deleting. For those items, we delete them out of the table, and that has the effect of unallocating those subnet addresses. That's it, simple as that. So we allocate CIDR ranges when we create a stack, and we deallocate them when we delete a stack. Now, I'm only skimming through the source code at a high level. If you do have software engineering experience, then by all means, please go through this source code and have a look at how it works at a detailed technical level. If you're not a software developer, if you're not a programmer, you don't really need to know how it works, just understand that it does and architecturally how it connects to CloudFormation. Now, lastly, let's look at the application environment 5.yaml. This is where the custom resource is declared and where the smarts happen to enable us to auto-select subnets. So let's scroll down. And I want to draw your attention to the auto subnet custom resource. Now, as I described in the theory lesson, we declare this as type custom : lambda auto subnet. As its properties, we give it a service token. And this service token is the endpoint for our lambda function. And we obtain it by doing an import value, and we import the value sharedinf -auto subnet ARN. And this, if you recall, is the export that comes from the auto subnet stack. So it's the ARN of the lambda function that's been created as part of the auto subnet stack. We also provide the custom resource with the DynamoDB region, and we provide this via a reference to the AWS region sudo parameter. We give it the DynamoDB table to use, and we obtain this by importing the DynamoDB table export from the auto subnet stack. We give it the VPC CIDR range that's in use, and we get that value by doing an import of the export from the shared infrastructure stack. So that's the stack we created at the very start. It's the VPC CIDR range that's defined within the shared infrastructure stack. We import that and we provide it to our lambda function. And then finally we set a debug equals true, and that just means there'll be additional logging which we'll look at when we create our first application environment stack. So everything else in the template is similar, apart from the fact that we've removed all of those parameter values asking for CIDR ranges, and we've replaced them, if we look at some of the subnets, we've replaced them by references to our custom resource and then the app public CIDR A value. And as we recall, that's what's returned from our lambda function. So we respond with app public CIDR A, public CIDR B, private CIDR A, and private CIDR B. And those attributes are referenced in our template using the get attribute function on the custom resource. Everything else is the same. All of the architecture is the same. We're just auto-allocating these subnet addresses. Well, thanks for listening, Cloud Gurus, and this is the end of part 1 of this lesson. If you do have any questions, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to finish this part and continue with part 2. Hello, Cloud Gurus, and welcome to part 2 of this lesson. This part continues immediately from where part 1 left off. So let's jump into it and get started straight away. So let's go back to our CloudFormation console, and I want to open a couple of tabs. The first is Lambda, so that's under the compute section. So find that and open that in a new tab. And the second is CloudWatch. That's in management, so open that in a new tab. And lastly, DynamoDB, which is in the database section. Again, open that in a new tab. And let's start by going to the DynamoDB tab and looking at tables. And we can see we've got a table here which is created as part of the auto subnet stack. If we have a look, there'll be no items in this table. The only mandatory attribute is the CIDR range, which is the hash key of this table. So when we automatically allocate any subnet addresses, we should see this table getting populated. And we're going to do that now. So let's go ahead and click on Create Stack, upload a template to S3, and let's pick the application environment 5.yaml. Go ahead and click on Next. And just look at how few parameters we have now. We still need to enter a stack name, so let's call this app-env test1. We can leave all of the defaults on, so it's a dev environment, it's version 1 of the application, min size, max size, and desired capacity can stay as defaults. Note that we don't have to enter any subnet addresses. So let's click on Next, Next again, and finally click on Create. So what's happening in the background is very important because this is where it differs from our previous template version. We start by creating a custom Lambda-backed resource. We pass this custom resource a number of properties, including a service token, which as we know is the Lambda ARN. So in the background, CloudFormation is passing information to Lambda right now, such information as the VPC CIDR range, the DynamoDB region, the DynamoDB table name, and other pieces of information. Our Lambda function is running in the background, determining which CIDR ranges can be used for these subnets. Once it's determined the ranges which can be used, it successfully creates. So if we click on the Resources tab, we can see that our custom Lambda auto subnet is in the create complete status, and that's because our Lambda function is executed, it's obtained 4 subnets to use, and it's returned that information to CloudFormation, which is accessible from the custom resource. If we go to the DynamoDB table and do a refresh, we can see the 4 CIDR ranges which have been allocated for use by this stack. We'll see each of our CIDR ranges, so it of course starts with 10.28.0, which is the first range available after the reserved public subnets of the shared infrastructure stack. And for each of these CIDR ranges, we record the stack ID that utilizes these ranges. If we go to the Lambda Management Console and select our Lambda function and click on Monitoring and put View Logs in CloudWatch Logs, and then click on this log stream, I've configured the Lambda function to output some diagnostic information. So it starts by saying the incoming event, and it lists the incoming event that's received by the function. And you should recognize the format if you've done the theory lesson. You'll see that CloudFormation sends a stack ID and a response URL, and then a resource properties block, which contains the attributes or the properties that we give to the custom resource. So the debug true, the VPC CIDR range, the DynamoDB region, the DynamoDB table. If we go back to our code and we look at the custom resource, that matches the values that we provide here. The critical one is response URL, and this is generated by CloudFormation when you perform any operations, and it's given to our Lambda function in order to send back the response. We can see that we allocate 4 subnets, 10.28, 10.29, 10.20.10, 10.20.11, and we send that response back using this response format. So we send it back to the response URL, and we return the stack ID, a status of success, a physical resource ID that we construct, a request ID that matches the request ID above. So we match a lot of these values to make sure that CloudFormation knows that we're responding to the same request. And that's all the information that we provide back to CloudFormation. So once CloudFormation has that information, it can finish creating the resource, and then all of our other resources can reference the subnet addresses that have been generated automatically by our Lambda function. And this is completed. If we go to Services and open the VPC console, we can even check that these subnets have been created just to make sure. If they hadn't, it'd fail, but if we do want to check that we've got them, we can click on Subnets, sort by CIDR range, and there we go. We've got 10, 28, 9, 10, and 11. Now what makes this good, apart from the fact that we don't need to manually enter these details, is we can go ahead and create another stack. We can use the same template, so application environment 5. We can say another app env test. We can deploy a different version of our code, but one that we know works, so say version 3, and then click on next and next again. Now what our Lambda function will do now is it will see that we've actually got those first 4 subnets allocated, so 10.28, 10.29, 10.20.10, and 10.20.11 have already been allocated to our existing stack. And the idea is that it won't reuse those because that will cause address clashing and will likely cause a failure. If we refresh again, we can see that our Lambda function has actually allocated additional CIDR ranges now. So we're now using 12, 13, 14, and 15 for this new stack. So we can see that these are the ranges in use by the new stack. So 12, 13, 14, and 15. If we go back to our CloudFormation console, we can see that this new stack is still creating. But what we can also do is delete our existing application env test1. And this will highlight what will happen when we delete a stack. So what will happen is it will start deleting all of the resources contained in the stack. Eventually, it will get to our custom resource, and it will send a delete request to our custom resource. What that will do is search the DynamoDB table and identify any CIDR ranges that are allocated to this stack. And when it finds those CIDR ranges, it will delete them from the table and then respond with a success, and that will allow CloudFormation to finish deleting this stack. So let's refresh this a couple of times and wait for this to complete. I'm going to pause the video and wait for this stack to delete, and then I'm going to return to the DynamoDB console and demonstrate those CIDR ranges have actually been deleted. So we've deleted almost all of the stack resources apart from our last remaining subnet, which is the subnet public B. And we can see now that finished, and our last resource was deleted, which is our custom resource. If we go to the DynamoDB console and refresh, we'll see the CIDR ranges that were associated with that stack have been deallocated. Now, one of the benefits of this automatic process is we can then go ahead and create a new stack, select the application environment 5 again, call this another test, accept the defaults, next, and create. And what we want to see this time is that the Lambda function will detect that we have IP address ranges before the ones that we've currently got assigned. So before 12, 13, 14, and 15, it should see that we have 8, 9, 10, and 11 free because they've been deallocated from the old stack. And we can see that is the case. It's reallocated those unused IP address ranges. So we've satisfied the criteria of this function. It's both efficient, it reuses unallocated IP address ranges, and it ensures that we don't have any IP address clashes. Now, Cloud Gurus, we're in a position now where we've actually resolved all 3 of these major problems. We don't need to manually enter lots of parameters. We don't need to manually allocate CIDR ranges, and our testing now works on stack updates as well as stack creates. So we now have an application environment template that can be used in an automated and scalable way. Now, to finish up, please go ahead and delete all of these stacks. So delete another test, delete another app-env test. When both of the application environment stacks that you've got have been deleted, go ahead and delete the auto subnet. You won't be able to do that until all application environment stacks have gone, otherwise it will error. Once the auto subnet stack has been deleted, then go ahead and delete your shared infrastructure stack. And as always, if you get any errors saying that it can't delete because of buckets which have files in, then just go ahead and empty those buckets and then delete the stack. And then after you've done that, just make sure that all of the buckets which have shared infrastructure in the name are emptied and deleted. Just make sure it's nice and tidy in your S3 console. So if I go to Services and open my S3 console, I'll see that I've got 4 leftover buckets. So app bucket, app bucket, app bucket, and Lambda bucket. Once you've deleted all of your CloudFormation templates, just make sure that you remove any of these which have got shared infrastructure in the name. Feel free to leave the CF template buckets as they're used when you upload a template to S3 when you create a stack. So don't bother deleting those. Just make sure you clean up the shared infrastructure buckets. Okay, so that's the end of this lesson, Cloud Gurus. I hope it's been useful, and I hope you can see the power of Lambda-backed custom CloudFormation resources. It really does give you the ability to code any extension to CloudFormation. The only limit really is what your imagination can come up with and what you have the capability to code. At this point, the application environment template that we have is fully automatic and fully scalable. And now that this template is capable of full automation, we can utilize it as part of the next theory and demo lesson where we're going to develop a provisioning self-service portal for the Cody's Development LLC business. These upcoming theory and demo lessons are going to be the last lessons in this section of the course, and it will really bring together all of the technology that I've introduced during this section and what you've learned in the last case study section. So I hope you'll enjoy it. Please make sure that you've deleted all of these stacks before you start on the next theory and demo lesson, as we'll start from fresh. We'll assume that you've got no running CloudFormation stacks. If you do have any questions on this lesson or any of the others, then please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. Hello Cloud Gurus, and welcome to this theory lesson where I'll be talking you through the architecture we'll utilise as part of the automated deployment portal proof of concept, which will form the last demo lesson of this section. Let's get started straight away and look at the architecture of our deployment system. So at a high level, the premise for this proof of concept is simple enough. Within Cody's Development LLC, we have a number of reasons a software application needs to be deployed. A developer might complete a new version and want to test it in an automated way. A test engineer might want to deploy a version of the application in order to run a full set of interactive tests. A pre-sales engineer might want to deploy the application quickly for client demo and trial purposes. And finally, the business might eventually want to provision and host instances of the application for customers within the business's hosting environment. So architecturally, the system has the following high-level components and entities. Firstly, we have our developer or pre-sales engineer who interacts with the provisioning portal, and they do so for a different set of reasons depending on their specific use cases, and this might be pre-sales, demos, testing, training, or code testing, to name just a few. Optionally, depending on that use case, we may also have a client who receives access to a provisioned environment, Now our system is supported by the Shared Infrastructure VPC, and this VPC provides networking services such as the VPC itself, shared subnets, internet and NAT gateways, and base-level connectivity to the internet. It's within this Shared Infrastructure VPC that all our application instances will be homed. As well as this, we have two S3 buckets. The first is the portal bucket, and this is where our portal code will run from, and an application bucket or app bucket, and this is where our application and test assets will live. It's the bucket where our CI, CD and build system puts any compiled or built code payloads at the end of its own integration and compilation steps. The scenario for usage of the system is that our initiating user, let's say it's a developer, QA or pre-sales engineer, opens the portal interface, and this is running from the web-enabled S3 bucket. From this bucket, they retrieve a HTML file which has some embedded JavaScript. At this point, the portal code is running on the engineer's local browser, and it begins by listing any applications available in the app bucket and any currently running instances of the application environment, and it does this by talking to CloudFormation and S3 using the AWS APIs. It presents both pieces of information to the engineer who is operating the portal. Once the engineer has this information, she can choose to interact in a few different ways. She can interact with existing stacks by deleting them, or she can provision new application environment instances. And the way that this works is that she selects one of the available application versions which are parsed from the application bucket. And she begins the deployment process by selecting an environment type based on this application version. The deployment process starts by communicating with CloudFormation, and it passes CloudFormation the application environment template that we've evolved throughout this section, which is going to be stored on the portal bucket. CloudFormation uses this information together with the exported information from the Shared Infrastructure VPC and the specific application and test assets to instantiate an environment within the Shared Infrastructure VPC. And once created, the engineer can either utilize this environment or optionally pass it on to a customer if it's a pre-sales environment. I think at this point it's worth taking a moment to understand how the enhancements that we've implemented together within this section of the course have accumulated in us being able to implement this level of automation with our application environment template. When we started, both the shared infrastructure and application environment templates were very unfriendly to automation. They had a large number of parameters which needed manual entry. Our application environment template is dependent on the shared infrastructure stack. It consumes services from the stack, specifically consuming values from it such as VPC, CIDR ranges, route table IDs, and URLs for the application and test bucket. By evolving it, we improve things. We first added cross-stack exports and references, and these allowed the application environment stack to consume shared infrastructure resources automatically without human intervention. And we also added advanced automation. We used CloudFormation custom resources and Lambda, and we did so to remove the need for anyone creating an application environment stack to have networking skills and knowledge of any other instantiated application environments. The CIDR ranges for the app environments are automatically generated by a Lambda function via the custom resource each time the app environment is used. And the result is a template where we have no mandatory parameters. You can enter an application version and an environment type, but the template doesn't need it. It has defaults for every parameter. It can operate without human involvement. Now, our proof of concept self-service portal will be built using 4 different templates. The first is the shared infrastructure template that we've been working on throughout this section of the course, and as described a second ago, it will provide the core shared networking and infrastructure needed for the rest of the system to work correctly. Next, we have a template which provides auto subnet functionality. It contains the Lambda-backed custom resource that we looked at in the last lesson. In addition, we also have a new portal bucket template which will configure a web-enabled portal bucket which provides the self-service portal bucket hosting. And finally, we have the application environment template itself, which automates the installation and configuration of the application on its server. And as always, my aim has been to provide a serverless architecture, where the only servers used are those running while some service or thing is being provided. In this case, our application environment will use an EC2 instance. All of the components will be run using serverless architectural patterns and managed AWS services. Okay, Cloud Gurus, well that's the end of this theory lesson, where I've provided a high-level overview of the architecture we'll use during the companion demo lesson. I can't wait to implement this with you. It's a lesson that we've enabled via all of the template evolutions that we've performed together. And it's an architecture that you'll be able to use within your own jobs, projects and businesses, especially in development and deployment style scenarios. Thanks for listening, and as always, if you have any questions on this lesson or any others, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next. And the next will be a demo lesson where we'll implement this architecture together. Hello Cloud Gurus, and welcome to the final demo lesson of this section. In this demo lesson, we're going to implement together the self-service deployment portal for Cody's Development LLC. Now, as I discussed in the theory lesson, the purpose of this self-service deployment portal is to allow developers, pre-sale staff, or QA engineers to deploy a specific version of the application into its own dedicated application environment, and then optionally, depending on the use case, to provide access to this environment to customers. We want to do this in a way that doesn't require access to the AWS console. Now, the reason that we're doing a deployment portal with this architecture is we want to provide a way for staff to deploy application environments without requiring access to the AWS console. The idea being that a member of staff without access to AWS can browse to a web page, click a button, and have a fully functional, provisioned application environment available within 5 to 10 minutes. And also that they can delete these environments from the same portal page, and that the environment can cope with tens or even hundreds of simultaneous deployment and environment teardowns at the same time. The idea being that this proof of concept tests a system which can support the whole development, pre-sales, and deployment processes of Cody's Development LLC. So let's get started, and as always, I need you to be logged in to the AWS account and have access to the lesson files for this lesson. Now you can either download those from the course GitHub repository or the resources section for this lesson on the Cloud Guru website. Either way, you need access to the 207 deployment portal folder. So let's go inside that folder and have a look at what's inside. So inside this folder, we have new versions of a number of the templates that you will have seen before. We've got shared infrastructure 4.yaml, which is the shared infrastructure template that creates the shared infrastructure stack. We've also got the application environment 5 template, which is the template that provisions each instance of our application environment. In the last demo lesson, we added the auto subnet.yaml template, and the auto subnet template extends the capabilities of CloudFormation by adding a Lambda function which backs a custom resource to automatically decide upon and store subnet allocations within DynamoDB. And then when the application environments are torn down, it releases those IP ranges for future reallocation to different environment stacks. Now, specific to this lesson, we also have portal.html, which is the HTML and JavaScript which provide our self-service portal functionality, and portal bucket and user, which create the web-enabled S3 bucket, and the user, which the self-service portal uses. So to start with, we're going to create our shared infrastructure stack, and I'm just going to step through the template at a high level while it applies. So create stack, select to upload the template to S3, and pick the shared infrastructure 4.yaml. Click next, call the stack shared infrastructure, leave all the other values as their defaults, click next, next again, and create. Now there's no major changes to the template which have occurred in this version. The template still accepts 3 parameters, a VPC side range, a public subnet A side range, and a public subnet B side range, and there's of course appropriate defaults for each of those parameters. Within the template, we're creating the VPC Internet Gateway, an application S3 bucket, a Lambda S3 bucket, a gateway attachment, public subnets, route tables, elastic IPs for the NAT gateways, and the NAT gateways themselves, one in each availability zone. Essentially, this template is the same shared infrastructure template that we've grown accustomed to over the last couple of lessons. And then obviously, in the output section, we output a number of critical pieces of information, so the VPC side range, the reserved ranges for each of the shared infrastructure public subnets, the ID of the VPC, the ID of the NAT gateways, the ID of the private and public route tables, the application bucket URL, the application bucket name, and the Lambda bucket. And of course, where appropriate, we're exporting the values for those outputs as stack exports. And that's as we've learned in other lessons, so we can access those using cross-stack referencing using the import value function. So that's the shared infrastructure template. So let's close that down. Now this may take 5 to 10 minutes to create. So while it does, I'm going to pause the video and I'll resume once it's finished. And at that point, we're going to upload the application and test bundles to the application bucket. And we're going to upload the auto subnet Lambda function payload to the Lambda bucket. Okay, so the shared infrastructure template is now created. So we need to go to the resources tab, locate the app bucket and open that in a new tab, and the same with the Lambda bucket. With the application bucket, as we talked about a second ago, we need to upload all of the application and test payload files. So go ahead and click on Start Upload, let that finish, and then close down the tab. And then with the Lambda bucket, we need to go ahead and upload the Lambda payload file. And that's the auto-subnet.zip file from the lessons file folder. Go ahead and start the upload on that one. That might take a little bit longer because that's a slightly bigger file. But once that's completed, you can go ahead and close down the tab. Just make sure that that has finished uploading before you do close the tab, because if this doesn't upload correctly, it will impact the functionality of the demo. So that's finished, so we can close the tab. And then we're going to create the auto subnet stack. And we know from the previous lesson that the auto subnet stack is a thing which imports the auto subnet zip, so the Lambda payload file. It imports that into Lambda. It creates the IAM role and the IAM policy that the Lambda function will use. It creates the DynamoDB table that the Lambda function will use to store the subnet allocation. And then it exports all of those values as stack exports that can be used from our application environment stack. So let's go ahead and click Create Stack, upload the template to S3, select the auto subnet.yaml file, click Next, name this one auto subnet, click on Next, Next again, accept the fact that it's creating an IAM role, tick the box and click Create. Now I'm skipping fairly quickly through a lot of these steps because we've done them before, we've done them in previous lessons. All of these steps so far, for example, we did in the lesson where we actually created this auto subnet extension to CloudFormation. So nothing's new, I'm just skipping through to get the system into a state where we can implement the specific new parts for this demo. So while that's creating, I want you to open up the portal bucket and user YAML. And this template creates an IAM user and associated access keys that will be used for the self-service portal webpage. So the self-service portal webpage uses the access rights of this IAM user to interact with AWS. We create the self-service portal bucket and an attached bucket policy so that anyone from the internet can access this bucket. And obviously in a real world scenario, you would lock this down to specific people or specific IP address ranges. However you wanted to do it, you'd lock it down. Potentially, you'd also have authentication on the self-service portal webpage itself. For example, if you used web federated identity and allowed staff members to log in with their OAuth username and passwords, that would be a much better situation from a security point of view. This is just a proof of concept, so having it open access is fine in this situation. And obviously we output the access key ID and the secret key so that you can use them to update the portal.html file, which is a self-service portal webpage. And just to make it easier, I've also created another output which provides the URL to the portal bucket and the portal self-service webpage. So that just makes it nice and easy. So once you've completed this, you can click on a link and access the self-service webpage. So we're going to go ahead and apply this template now. It doesn't have any dependencies on other sections of the infrastructure, so to speed things up, we may as well apply it straight away. So go ahead and click on Create New Stack, upload the template to S3, and pick the portal bucket and user.yaml. Click on Next, and call this portal bucket and user. There's obviously no parameters, so just click on Next. Next again, acknowledge the IAM capability requirements. In this case, it's IAM access key and IAM user. Accept that by ticking the box, and click Create. We'll wait for that to complete and then proceed to the next step. And it's at this point where we're starting to implement things specific to this lesson. So far we've created the shared infrastructure stack and the auto subnet stack. And both of those have been defined and implemented in previous lessons. They just allow the new version of the application environment stack to apply without any human intervention. So that's nothing new for this lesson. What is new is the portal bucket and user and the step that we're going to perform next. So once this is created, we're going to be performing steps unique to this lesson. And that's created now. If we go to outputs, we can see that we've got an admin key and an access key. You will obviously have unique ones for each of those in your environment. Don't attempt to use these as they won't work. I'll be deleting this stack as soon as I finish recording this lesson, and they will no longer be valid. You'll need to apply this stack yourself and then use your own access key and your own secret key for the next step. So click on the Resources tab, and I want you to open the Portal bucket in a new tab. And the Portal bucket is going to be the S3 bucket where we upload the Portal HTML file and the application environment template that will be used to instantiate stacks of the application environment. So I want you to go ahead and click Upload and upload app-env5 to this bucket. And there's been no changes to this application template. We're simply uploading it to this bucket so that we can access it pragmatically from the portal.html file. And I'll show you that in a second. So go to the lessons file folder and open up the Portal HTML file in your favorite code editor. I'm going to use Visual Studio Code. Now this is a HTML file and it's got embedded JavaScript, and the embedded JavaScript utilizes the AWS JavaScript SDK. And it does that so that it can communicate with various AWS endpoints. In this example, CloudFormation and S3. The first thing we need to do is to supply it with authentication information and our current region. So change the region change me to US-East-1 or whatever region you're deploying this demo into. Then you'll need the access key and the secret key. And you can get those from your AWS console, in the Portal bucket and user stack, and then outputs. So let's start with the access key ID. So copy that into your clipboard, go back to the editor and replace this placeholder. And then return to the console and then do the same for the secret access key. So copy it, make sure you've got it all. Return to your code editor and replace this placeholder. And just make sure, as you can see on my screen, I've made a mistake. Just make sure that you're only pasting in the actual secret key. And just confirm that both of those details, so the access key ID and the secret access key, are correct. They'll be used to authenticate to AWS, and so if they're wrong, the demo won't function correctly. The same with the region. This needs to be the region that you're deploying this demo into. Now the last placeholder that we'll need to change is the template URL. And you can get the template URL from going back to the Portal S3 bucket where you uploaded the app-env5 to, select it, click on Properties, and you'll need the link. So this link, the direct link to this file. So copy that into your clipboard, go back to your code editor, and paste it in place of this placeholder. And a lot of the time what happens is it does damage the formatting, like we can see there. All you need to do is make sure that this template URL is surrounded by 2 single quotes and that it's the actual URL that you just copied. If you've got syntax color highlighting, just make sure that there's no errors and that the color is as you'd expect. So in my case, it's a cyan color for the key and then an orangey brown color for the value. So we can see that that's correct. It's pasted that in and it's surrounded by single quotes, so we're all good. So save that file, just have one final check. The template URL's good, the region's good, and then the authentication information, so the access key ID and the secret access key is correct. Now I can't assume any specific software engineering skills in any of my students, so I'm just going to step through what this does at a high level. And I'm just going to start by minimizing some of these functions so that I can talk through how it actually works. So we actually have on this web page 3 distinct areas, or 3 distinct areas of the web page. We have one that I call buttons and boxes, one that I call results, and one that I call prov area or provision area. And I'll refer back to those in a second. Just be aware that there's 3 distinct areas of the web page. The first thing we do at the bottom of this page is to do a list stacks call. So it calls the list stacks function. And if I expand this function so that we can read what it does, don't worry if you're not a software engineer or don't worry if you've not got any development background. Just let me talk you through it and you'll understand what it does. The first thing is that we perform a list stacks operation. And we list any stacks that are in the following states. So this is a list of states that are valid for CloudFormation. And we connect to CloudFormation using the access key ID and the secret access key. And we say perform a list stacks operation. And we make a variable called stacks equal to this output. So it's essentially a list of stacks. And then we make a variable called HTML. And inside this variable, we start creating a table. So we make a table and we've got headers such as stack name and creation time, and then a column called delete. And then we look at each one of these stacks that we listed from our environment. And we say that if the stack name starts with CD LLC, which stands for Cody's Development LLC, if it starts with that piece of text, and I'll come back to why in a second, then add a line in the table listing the details of that stack, and having a delete button which calls the delete stacks function. For any stacks that don't start with CD LLC, we deem them not to be Cody's Development LLC stacks, and we ignore them. Then once we have this block of HTML, which is a table, we use jQuery and we set the results area of our web page. Remember I said that we have 3 distinct areas on our web page and one of them is called results. We use this to set that results area equal to the HTML that we've just generated, so the table listing all the stacks. The next thing we do is run the function list apps. So let's minimize list stacks and we'll go to list apps. And what list apps does is it pulls in the name of our applications bucket using the stack export. So using this cross-stack reference export feature, it obtains the name of our application S3 bucket. And then it performs a list of all the objects in that bucket, and it looks for the individual application versions, and that's the app1, app2, and app3.zip that we've uploaded to that bucket. And then what it does, similar to the list stacks, it makes a HTML object, and it makes a table that lists each one of those application versions, and then a button to provision a dev version, a test version, a prod version, or a pre-sales version of that specific application. And when that button's clicked, it calls the provision stack function, which we'll talk about in a second. And then we take that HTML, which is a table, which has a row for each application version, and we output it to the prov area, which is the third of the areas that I talked about on the screen on the web page earlier. So this prov area, we output this HTML into that prov area. So that lists on the web page a list of all the application versions, and in the table has buttons to provision those applications. And then I mentioned 2 other functions, one called delete stack, and delete stack is supplied with the name of a stack, and with that name it connects to CloudFormation and deletes the stack. Nice and simple. Now provision stack is a little bit more complicated, and how this works is the provision stack function is provided with an environment type, so dev, test, prod, pre-sales, and it gets those values because remember the user of the portal is clicking, for example, on the dev button next to application version 1. So the provision stack function always gets the environment type and the app version. And then this code segment is making a UUID, which is a universally unique ID, and that's just to make sure that we can't have any clashes of stack name within our account. It takes this UUID and it adds it onto the end of a CD LLC prefix. So every stack we create using this function will be called CD LLC and then a unique ID. And it takes this together with the environment type and the application version, and it directs CloudFormation to make a new stack using this template URL. And this template URL is our application environment 5 template. Well, thanks for listening, Cloud Gurus, and this is the end of part 1 of this lesson. If you do have any questions, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to finish this part and continue with part 2. Hello, Cloud Gurus, and welcome to part 2 of this lesson. This part continues immediately from where part 1 left off. So let's jump into it and get started straight away. Now I've mentioned before in the course that for any templates which have parameters, you either need to supply a value for that parameter or it needs to have a default. And all the work that we've done on this template to date has been so that the template can be applied without having any mandatory parameters. So all we supply is the environment type and the version of the application, and everything else is automated in the background. So we run a CloudFormation create stack. We pass it all of those parameters, so the environment type, the application version, and the template URL, and we direct CloudFormation to create a stack with those details. And then after we run that, we call a list stacks to update the web page. And that's pretty much it. It's a simple, fairly insecure, proof of concept self-service portal. So now that we've updated those values, close down the web page and upload it to the portal bucket. So add files, portal.html, and click on start upload. And then go back to CloudFormation. Make sure the portal bucket in use is highlighted, and we can go ahead and just click on this URL. And this will open our self-service portal in our web browser. And I apologize for the fact that it's fairly ugly, but as I just spoke about, it's essentially loaded a list of the stacks within our account that have the prefix CD LLC, which of course at the moment is none. And then it's done a list on our application bucket. It's identified 3 versions of our application, and for each of those versions, it's given us the option of deploying dev, test, prod, and pre-sales. Now, if you want to verify that this is indeed dynamic, if we open our lessons file folder, go into our apps, and for app3.zip, do a copy and a paste. and then rename that app4.zip. And do the same for the test version 3. So copy test version 3, make a copy, and call it test4.zip. And just obviously make sure that you don't have a double extension. And then if we go back to our S3 console and look for our application bucket and go ahead and upload version 4 that we just created artificially. So start the upload. And then if we go back to our portal web page and do a refresh, we'll see that it loads up 4 versions now. So you can see that this web page is completely dynamic. Each time it loads, it's looking at the application bucket, determining which versions of the application we have, loading them in and presenting this table with version and then the option to deploy a stack. So our page is loaded. It's done a list of any stacks which match the criteria of being prefixed by CD LLC, and that's none. And then it's enumerated the application bucket, listed all the versions and produced our table. And that table allows us to deploy versions of the application. So let's start by clicking on the dev button next to version 1. Now in the background, that's gone ahead and talked to CloudFormation. It's given it the directive to use our application version 5 template, and it's provided it with a number of parameters, so version 1, and that we want to deploy a dev environment. And we can see that straight away, it started that provision, it's got our creation time, and it shows create in progress. Now we can go to our CloudFormation console and do a refresh, and we can see that that's actually in create in progress. We can see it's in the console. Obviously our self-service portal users wouldn't have access to the console. That's the sole reason for creating it. But we as administrators can see that we've got this template. It's creating, it's making a stack, and it's listed as create in progress. Now that will take a few minutes to complete, so I'm going to pause the video and I'll resume once this stack is created. So our stack's reached create complete status, and it's gone through the same process as I demonstrated when I talked about the auto subnet lambda function. So in the background, it's used the lambda function to allocate the subnet IP ranges. It's stored them in a DynamoDB table. It's used them to create the subnets in the template, and then it's pulled in any of the other values that it needs from cross-stack references. So even though we've instantiated this stack from within the self-service portal, so outside of the console, it's still gone through exactly the same process that we've talked about to date. If we click on the Outputs tab, we can even see that we've got the value to go to the Elastic Load Balancer to access the application. And if we go ahead and click on this, we can see Hello World working version 1, so we know that it works. Now returning to the self-service portal, we've also got the option to click on the delete button, and that will initiate a stack delete operation, so we can see that it's changed to delete in progress. Returning to the console and refreshing, the status is mirrored. We've got delete in progress. So there's definitely a link between the self-service portal and the CloudFormation console. They're both interacting with CloudFormation over the APIs. Now one benefit of evolving the application environment and the shared infrastructure templates to the point where they're fully automated is that we can create environments faster, much faster in fact, than if it required manual parameter entry. Just imagine for a moment that this web page is being accessed by 10 or 50 different engineers, or even an automated deployment process. Imagine if each one of those people or processes needed to calculate the subnets required to provision the application environment. It would severely limit the rate at which we could deploy environments. Now at this point I want to demonstrate just how quickly we can provision environments using this method. I don't recommend that you perform this step in your own environment, as it does have a cost attached. It will be fairly small, but what I'm going to do is click on this button several times in succession to create several environments rapidly. Now the minimum cost from AWS's perspective for running any environments is 1 hour of service for all of the products used. If I click on dev, it's going to use 1 hour of instance time for our EC2 instance, and it's going to use 1 hour of time for our Elastic Load Balancer. Now these costs won't be excessive if you stay to the dev environment type, but just to reiterate, you can either follow along in your own environment just to have experience of how quickly and rapidly these can be deployed, or you can just watch me do it. In either way, I'm just going to randomly click on this dev button. And I've immediately provisioned 6 environments, and I've provisioned those environments as quickly as I can click the button. In the background, each of these environments will be provisioned via CloudFormation, and it will use our auto subnet lambda in the background to provision those subnets. If we go to DynamoDB and open in a new tab, and just look at the table that's used for subnet allocation, we've definitely got multiple entries in there. It's able to provision and allocate those subnets as quickly as we need them. If we go back to our web page, we can just as easily click on delete on all these environments and set them all to delete. And then again, in the background, in the CloudFormation console, they all go to delete in progress. Now, it's possible that if you do create this number of environments, you may get an error on one of the stacks. And that error may be that you don't have sufficient capacity in your account. There is a limit on the number of stacks you can have, the number of load balancers you can have, the number of EC2 instances you can have of various types. And these are soft limits, so you can upgrade them via AWS support, but you may have a limit. So just keep in mind that if you do create anything than say more than 5, you might get some errors. So I would tend to limit my click spam in this case to about 5 so that I don't create any more instances than my account can support. And of course, if you want to expand this, you can lodge a support request and get any of these account limits upgraded. And at this point, we've finished this lesson. This is the last demo lesson in this section and the last demo lesson in this course. What you've done in this section is evolve a template which was capable of very limited automation, and you've made it so that it can be applied in an automated and highly scalable way. You've created a self-service portal that can be provided to people who don't have AWS accounts, and it allows them to provision application environment instances with a specific version of the application. We've talked about how we can use creation policies to implement custom application testing. Now, all of these things together, whilst they're simple examples, and they have to be as part of this course, every example that I've used is capable of being expanded upon to a production setting. So you can redevelop this proof of concept self-service portal, add some authentication and some additional niceties and use it in production. And you can expand the testing that we've got as part of the application to include some actual rigorous application testing. And this design pattern or this architecture pattern is one that I've helped implement in many development companies as part of their CI, CD and production deployment pipeline. Now, before you complete this lesson, allow these stacks to delete, and then delete the portal bucket and user stack, delete the auto subnet stack, and delete the shared infrastructure stack. And again, if you get any complaints about S3 buckets not being able to be deleted because of contents, then just go to the S3 console and manually delete the buckets. And afterwards, just clean up any buckets that you've got outside of these CF-template buckets. Now, I hope this lesson was useful. If you do have any questions, please reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to the next.